Okay, with that announcement, I would like to now take up this course. So, what you will learn in this particular course? Okay, let us get the whole the structure of the course here. There are IEC 6150 and 61511 fundamentals we will learn. See, this is a one course, and this has one day course, and this is basically sort of trimmed down to a size of about 60 slides. But original, the basic course is requires about 3 days. So we will be touching on most of the topics. We may not be able to have the time to discuss in detail, but wherever your questions are, please post in the questions, and we will try to attend to all those questions. And next couple of days, we'll answer those questions. Okay. Now, the second part of the thing is functional safety life cycle and management. We are going to go in detail because this is a very important topic, and there is lot of ignorance about this topic in India. So we'll explain both the functional safety life cycle. Then till basics and till determination, what is the process that we may not be able to hands-on do the workshop, but we will be telling you the whole process. We'll explain the whole process. Then things like risk matrix, HAZOP and LOPA basics we'll explain. Then some methods, qualitative and quantitative, semi-quantitative methods of risk assessment that we'll explain briefly. Then what are the various steps after you decide that what is your SIL design, SIL verification, SIL validation. These are very important milestones, which will cover those also briefly. Then one very important topic is lot of people they ask about what is certification. So we will explain this concept in detail. What is the certification, how it is done, and what are the documentation to be looked into. Okay. And then some practical functional safety applications we will see if time permits. Okay. So this is broadly the long and short of the course. So let us get into the course. Yes, this is the agenda. Today's course we have divided into 4 parts. Part 1 is fundamentals and standards. So introduction to the training and course of overview. That is the first part. The second part in part 1 is overview of IEC 6150 and IEC 6150 standard. The third part in part 1 is risk concepts and process plan design fundamentals, role of regulatory bodies, insurance bodies, and layers of protection. These we will explain. Then part 2 will cover this functional safety basics like IEC 6150 and IEC 6150 life cycle, functional safety management, and the introduction to SIL safety integrity levels and SIL tables. So these are very important concepts. So please pay attention when I am explaining these things. Next part. Part 3, we have this risk management techniques will cover risk matrix and HAZOP session, LOPA session, risk graph method will cover quickly. Then safety requirement specification, what it is all about, that will explain. SIL design, verification and validation. These all concepts will clarify. Then finally, certification, as I mentioned to you, certification and application. SIL certificates, how to read them, how to understand the SIL certificate. And finally, if time permits, we will have a good discussion. But this is by and large the 4-part course today. Okay. If all of you agree, then we'll jump straight away into the session. Okay. Yeah, emergency preparedness. In case of emergency, any kind of emergency, please be prepared for that. And this preparedness, as explained here, is about the basic information, the various siren types, evacuation routes, and assembly. So, as per your guidelines or wherever you are attending from, please follow that. Next slide, please. Okay. Now, straight away jumping into the course, fundamentals and standards. Okay. Introduction to the training course. My introduction already Shadini has given. By and large, I have my recently completed 78th birthday. So I want to continue as long as possible in training and function safety and this area. Okay, because that's a very interesting area. It saves lives. So that is something very important. Industrial world, we see that unnecessary lot of lives are lost. If we can save even one life in your lifetime by training some people, that would be a huge thing I would consider as my achievement. Then, as explained in the slide in the 3D, the section is divided into four parts. Part one and two are more to recap your concepts. Part three is the core part which explains important aspects, and part four explains the certification aspect. In part four, we are going to break up. That was the original idea, but now we do not think that we'll be able to break up into breakup rooms and all. So we'll see how the time permits, but at the moment I do not see that it is workable. Next slide. So, okay, brief history. Let me quickly capture the brief history of how this functional scientist started. Okay, so way back in 1988, there used to be a oil and gas platform somewhere near Aberdeen. Okay, and in North Sea, and it was owned by Occidental. The name of the company was Occidental. Okay, and initially it was a oil platform. See what they do, they go to the seabed, make a drill, and if there is a oil which is already established by geotechnical studies and all, that oil is found in that place. So then the oil starts gushing out from that particular place where they have done the drilling, and then it is subsequently taken out onto the platform. Then after processing, it is storage is made, and then subsequently various processes are there. So initially, this was a huge platform. Piper Alpha was a huge platform. At that time, it was taking care of about 10% of the United Kingdom's oil and gas needs. Okay, and then subsequently, what happened? They found that oil, along with the oil, gas is also there. So they did some minor modification on the platform in a very hurried, unstructured way, and they just added some additional modules on the platform, and then they converted it into a oil and gas platform. Now you please understand that oil, when you are handling, you have a one type of hazard, and what is that hazard? It is a fire hazard. Why? If you are handling gas, you are coming into different type of hazard, which is called explosion. Okay. So fire and explosion, these are two different types of hazard. They need to be handled differently. Now, in hurried way, Occidental, this Piper Alpha oil platform was converted into a oil and gas platform. And in doing that, they did not pay full attention that actually when they are converting the platform from oil platform to oil and gas platform, all the precautions were not taken. One major precaution they forgot to take was there should have been, there were accommodations, living accommodations were there on this platform. So between the living accommodations and the control room, earlier when it was only an oil platform, there was a firewall. Okay. Now, since they converted into oil and gas platform, they should have installed a explosion wall, explosion protection wall. Okay, which is done by different standard. By its total design is quite different. Okay, they forgot to do that. So what happened? As I'm going to explain you the how that accident terminated, you will come to know that the first thing what happened when the accident happened, the control room was completely gone. Okay, so let us first understand how the accident happened. Okay, the oil, as I mentioned, it is coming from the oil well, and it is pumped by. There are various pumps on the oil platform. One condensate pump on oil carries a lot of condensate pump. One of the condensate pump has been removed for maintenance. Say, and it has a standby pump. Pump A and pump B. That was the situation. Okay. So temporary blind plant was fitted onto the pump A, and the pump B was started. But in those days, we are talking of 1988. Try to take yourself into that 1988 time frame. So what used to happen? work permit system in the control room was not very well organized. Okay, so poor work permit to work and communication during this shift change did not hamper the actual transfer of knowledge that Pompeii is under maintenance. So unknowingly, in the next shift, the operator started pump A when because pump B started giving some problem, and the moment pump A was started because there was a loose flange connected at on pump A condensate pump, so immediately the gas started leaking out from that place, and within no time it got some fire somewhere, and there was a huge explosion. And as I mentioned to you earlier, there was no explosion protection wall. So the moment that explosion happened, first thing what went down was the control room. Now just imagine you have a huge explosion and fire on the platform, and you do not have any control room to take any preventive action. What will happen? Immediately the whole fire got into very big proportion, and as I mentioned to you, there were living accommodations on the platform. So immediately the people started jumping from the platform into the sea and things like that. And ultimately, the end of the thing was about 167 people died in this platform, in this particular accident. Next slide. Evacuation was severely hindered by smoke, heat, and lack of clear procedures. Many personnel were trapped in accommodation areas and not designed for such scenarios. The disaster led to public inquiry chaired by Lord Cullen. The UK Parliament, what they did, they immediately appointed a investigation committee, and Lord Cullen was the chairman of that committee. Resulting, this Lord Cullen committee gave a landmark Cullen report on this particular incident, and the report made, which was published in 1990, it gave 106 recommendations, fundamentally transforming offshore safety regulations in the UK. Okay. Now, key outcomes including shifting from prescriptive to goal-setting safety regulations, introduction of safety case regimes, improves permit to work system, enhance emergency response planning, and clearer operational accountability. The incident remains a defining case study in the process safety risk management worldwide. Okay, so this is the importance of this Cullen report and this Piper Alpha particular incident. Okay, now as explained in the previous slide, Lord Cullen committee gave 106 recommendations about how process safety should be addressed. The report was published in 1990. Now, International Electrotechnical Commission, which is an international body, which has got a signatory of 199 signatories are there, and its headquarters is there. Okay. This also set up a working group called TC65 was established, and it was established in late 80, okay, 1980. And a draft functional safety standard was under preparation. The Lord Cullen report became very handy for this particular committee, TC65, and they adopted this particular 166 recommendation as it is. Okay. And you can find this Lord Cullen 106 recommendation. They strongly influence the broader safety culture and the regulatory thought process of the IEC 6150 drafting committee. This TC65, whatever standard they came out with, was called IEC 61508, and which is a mother standard for functional safety, and was published in 1998. First publishing of IEC 61508 was in 1998. Okay. Now this IEC 61508 standard it has got 7 parts. Let me explain you what are these 7 parts. Okay. And there are subsequent revisions of the standards, and the latest standard of 2010, which was published by IEC, it has got 7 parts. The first part defines the general requirements of functional safety standard. Then second part is requirements for electrical, electronic, and programmable electronic systems. It is very commonly called in the industry as EEP, you will find that everything has got a combination of hardware and software to take care of any such incidents. Okay, so part two talks mainly about hardware. Okay, part three is about software requirements. We are going to implement safety by using hardware and software. Okay, so part two gives you all directions regarding how the various aspects of functional safety are to be treated when it comes to hardware. While part three talks about software requirements. And part four, there are many definitions. This standard IEC 61508 standard is a very big standard. All you guys must really read this once you are going to work in functional safety. Okay, and this part 4 gives lot of definitions and abbreviations. Lot of explanations are required because this was written in such a way. It's a very vast topic and requires lot of going back and forth in the standard. So requires lot of definitions and abbreviations. Then part 5 is the examples and methods of determining safety integrity level. We are going to learn about the concept of safety integrity level. So this part 5 talks about that. Part 6 talks about guidelines on application of part 2 and part 3. See, part 2 and part 3 gives you definition of how hardware and software is to be handled. And part 6 gives the guidelines when you are actually working on functional safety in a real scenario, how to interpret this part 2 and part 3 recommendations and how to implement. Okay. And part 7 is the overview of techniques and measures. These are in our detailed course, we cover a lot about these techniques and measures. Right now, we just understand that these are certain recommendations given by the standard how to handle various cases when you are actually practicing the IEC 61508 standard. Okay, thank you. Now, overview of IEC 615. There is another standard. See, IEC 61508 standard is a mother standard, I said, as I mentioned to you. IEC 61511 is an application standard. Okay, so this was subsequently published 2003, and the first edition of IEC 61511 came in 2016. Okay, and it has got three parts. Part 1 is the framework definition of systems, hardware and software requirement. Part 2 is guidance for application of IEC 61511 Part 1, and Part 3 guidance for determination of the required safety integrity. So, as you can see, in the previous slide we saw that part 6 talks about this SIL levels and all, and part 3 in IEC 615 gives you guidance on for the determination of required safety integrity level. Okay. Now, the relationship between, you might get confused, a lot of people get confused. What is the relationship between IEC 61508 and IEC 615? For your understanding, a very simple explanation given here. Process sector safety instrumented system standard. We have two routes we take for manufacturers and suppliers of devices. See, when you are implementing a safety instrumented system, you need systems or devices which are to be manufactured or developed by some agency. And second part is once you have this developed parts which are as per IEC 61508, then they have to be used and implemented in a safety instrumented system. And that work is done for the user. Users, that means plant users like a refinery or petrochemical plant or a oil and gas facility. So for the users, it is his requirement that he wants a safety instrumented system. So the user actually implements the system, but he is mainly focused on doing his business related, manufacturing petrochemicals or chemicals or oil and gas or whatever it is. So he is focused on doing that work, but he needs this safety instrumented system to make things happen in his particular plant. But there are system integrators who will deliver this system to him, or the users or the consultants and all, they will be there participating in this implementation of the functional safety system. So this is the difference between these two standards. IEC 61508 for the manufacturers and suppliers of devices, while IEC 61508 is the application standard, which actually is for more users or integrators or consultants, those type of agencies, they are more likely to use. Okay, next slide. Now, as I told you, IEC 6150 was the first standard which was developed for functional safety. Okay. And functional safety has many applications. Okay. And all these applications are covered under one umbrella. And IEC 6150 is the mother standard, also called the umbrella standard, which is guiding principle for all these standards below it. Okay. All diverse standards like process industry, nuclear plant, and profiles for safe communication, gas detection, power drives, medical software, EMC, humidity for functional safety, ISO automotive standards, then machinery standards. These are all somewhere, even railways, they are borrowing from IEC 6150. Okay, next slide, please. Now, when to use IEC 6150 and when to use IEC 6150, we find confusion at least in India about when to quote IEC 6150 and when to quote IEC 61511. So, following explanation may help. If you are manufacturing products or developing products, then use IEC 6150. Therefore, a product manufacturer may use IEC 6150 to ensure compliance to Part 2 if he is developing only hardware, and Part 3 if he is developing only software. And if he is doing a combination of hardware and software, then both Part 2 and Part 3 he has to follow. Also, their work processes need to align to with various parts of IEC 6150. The certification of the product is as per IEC 61508. Okay. Now, IEC 6151 is in reference when you are engineering consultant preparing a specification as a system integrator, integrating a safety solution, system solution, and want your work to be compliant to IEC 6150. Now, any questions what you are getting while I am explaining this, please post them in the chat box. Okay, and we will try to answer to all those questions next 2-3 days. Okay, next slide, please. This is the chronological history of IEC 6150. Okay, so as I mentioned to you, Germany was way ahead in functional safety. Okay, so the first PEV certified safety system was certified in 1970 when even IEC 6150 committee was not in action. Okay, so IEC 6150 committee started developing IEC 6150 standard in 1989 and came up with the first release of IEC 6150 standard in 1998. Okay. In 2003, first release of IEC 6151 standard happened. 2010, the second release of IEC 6150 happened. And 2016, second edition of IEC 6151 happened. These are revisions, and we are expecting that very shortly, maybe 2026 or 2027, the second revision of third revision of IEC 6150 will forward. Okay. Now, before I go into this concept, I would like to explain some of the concepts which are not covered in the slide but which are necessary for you to understand. First thing is, I am talking about functional safety, but this word is not very commonly heard. Okay, so let me explain you that functional safety, for the sake of this course of study, more relates to process safety of the plant, and it is relevant to design of processes, plant design, operation, maintenance of equipment, standard operating procedures, documentation, safe operating and shutdown procedures, prevention and mitigation of hazards related to basic process control, safety instrumented system, emergency shutdown system, all of this put together. Okay, so this is a very comprehensive way to express what is functional safety. Okay, and what we are saying, functional safety is a science which is more dependent on reliability science. Okay, it's an offshoot of reliability science, and reliability science is a branch of mechanical engineering. Okay, so please understand it that way. Now, coming to the next concept. concept of, see, there is a, once you have this commonly used concept of functional safety, there must be a proper definition of it. So CCPS is a Center for Chemical Process Safety. They have given a very beautiful definition, which you can please listen carefully and understand. Functional safety is the part of overall safety of a system or a piece of equipment that depends on the system or equipment operating correctly in response to its inputs, including the safe management of likely operator errors, hardware failures, or environmental changes. See, what we are going to discuss today is very important from risk perspective. Okay, we are talking about what is risk, how risks are undertaken or handled in operating plants, and what should be done in case of there is an accident, which actually means nothing but a hazard which you are day to day living with, but which, because of certain extraneous situations, get converted into an accident or incident as you call it. Okay. So we do not want that hazard to get converted into an incident or consequence, but because of certain things beyond your control, it happens. And that's why we like to study the risk of a plant. Okay. So this risk concept which I'm going to explain to you is very important and please understand it. Okay. ISO IEC Guide 51 defines safety as freedom from unacceptable risk. Okay. So question may come in your mind once you hear this particular definition, freedom from unacceptable risk. You may say, what is unacceptable risk? That means there should be some risk which is acceptable. All these kind of questions will come, but that is unimportant. Okay. What is important? What is important is first to understand what is risk. Okay. Very few people very properly can mention what is risk. Okay. So for everybody's benefit, I will make a statement which you can verify later or now also. Risk is nothing but a multiplication or a combination of frequency and consequences, F into C. Okay. And the resultant is called a risk. And it is a mathematical quantity. It's a can be expressed in mathematical terms. Okay. That's how I have expressed it here on a graph. Okay. The graph has two axes. One is y-axis and the other is x-axis. On x-axis, I am taking consequence. On y-axis, I am taking frequency. Frequency means what? Frequency means if an accident is going to happen, at what frequency? Whether it will happen every day or it will happen once in a week or once in a year or once in 10 years. What is the likely frequency of that accident? And consequence is what? How big it will be. How big it will be. Suppose whether it will result into a small fire or it is going to be an explosion or it is going to be a huge fire. Okay. So depending on that, you define the consequence. Okay. Now, every organization defines what is acceptable risk to them. Okay. How they define it? Once I have expressed it here as a frequency and consequence graph, you can say the organization draws a line. The line is shown here.
Yes, line is shown as this. Yeah.
This particular line, which this is the line which is shown. This is the line drawn by each corporate. Okay, it has a method. It's not just like arbitrarily, it is not drawn. The organization considers many factors before drawing this line. And below, if the risk is below this line, it is acceptable. And beyond this line, it is not acceptable. Okay. And now I have shown one existing risk point here. Okay. And you can see that this is the existing risk, which obviously is beyond my tolerable risk. So what I do, I find that my present risk is so much beyond the my acceptable risk. Okay. So this is the gap. When you are doing the ad hoc and this study, this gap first we identify. Please try to understand. This gap we identify in all these risk studies and then try to put various barriers here by defining various barriers. We are shortly going to explain the various layers of protection. Those layers of protection, they act as various barriers so that by putting these barriers, we bring the existing risk, which is much beyond the tolerable band. It is brought to the tolerable part by putting these various barriers. This is the concept of risk. Okay. Is this concept of risk understood by all of you? Please look at this slide. Just try to grab this slide, understand this for a minute. I'm giving you 1 minute to grab this particular slide. Okay, because this is very important.
Yeah. Okay.
Okay.
Okay. So
People have raised thumbs. So
yeah, yeah. Thank you. Thank you. Yeah.
next slide, please. So properties of risk. Now, since you understood the risk, what is the concept of risk? Let us understand what are the properties of risk. Risk is a perception. First, understand this. Risk is a perception of any individual or a society or a corporate entity. Okay. So risk is therefore subjective to a specific individual, society, or corporate person. See, driving in city is acceptable to me. Okay. When I drive my car, I'm an old person. When I drive my car within my city, it is acceptable to me. But if suppose somebody tells me, I'm still staying in Vadodara, in Gujarat. Now, if suppose somebody tells me that Mr. Mohan, you come down to Mumbai by taking your car and driving it, I will not do that. I will say no. I can take the risk of driving a car only within Baroda, but without beyond Baroda, between driving on the highway between Mumbai and Baroda, I do not want to take that risk. That is my perception of driving. Car driving is an activity which involves risk, and my particular perspective of that risk is that I accept it within my city, but I do not accept it when it is outside Baroda, between Mumbai and Baroda. I do not want to do that. So we saw in previous slide that the risk is mapped from x and y axis, therefore it can be assessed mathematically. One may be able to measure the express risk numerical terms. Yes, this is possible. We are going to touch upon the LOPA analysis. There will show you a semi-quantitative method of analyzing risk and expressing risk. Okay. Next slide, please. Now, these are the layers of protection. Two slides back, actually, we showed you that the existing risk is beyond our acceptable risk, and then we put various barriers. Okay, as you can see here, these are the various barriers. Okay, these barriers are typical layers of protection, which we are now going to explain. Okay, by putting in these barriers, we are reducing the existing risk and bringing it to our acceptable domain. Okay. So now let us understand the layers of protection concept. Here I am going to explain to you 7 layers of protection. And what are the 7 layers of protection? The innermost layer, as you can see, this looks like a field of onion. Okay. So, or cutaway view of an onion. Okay. So the innermost layer, as you can see, is the process layer. What does it mean? It means that process is designed if it is perfect. Okay. It's never possible because in various plants like petrochemical plant or oil and gas plant or whatever plants you are working, we are producing something by transforming it from one particular phase to another phase by increasing the pressure or temperature or whatever parameter, so that such a transformation from one phase to other phase always involves some risk. Okay, so 100% safe process design is a ideal thing. It is not practically possible. Somewhere you might be going into a higher temperature zone or higher pressure zone or vacuum zone or something would be there. So theoretically, ideally you can have a very 100% safe process design, but reality it cannot be done. But you can come very close to that. So if you have got a very robust process design, you may not need all these layers of protection, but some few layers only you may need. But some of the layers will always be required. Okay, so process plant design layer is the first layer of protection. If your process plant design is very robust, you may not need all the rest of the six layers, but for sake of explanation, I am going to explain all these seven layers. Okay. Next layer is basic process control system. Okay. In short, it is called BTCS. Okay. Now, what is it? See, once you have designed your process for a particular temperature, process, pressure condition, their process is a dynamic thing. Okay, that process keeps on continuously dynamically moves these parameters. The temperature may go up or down, the pressure may go up or down, and it is needs to be continuously monitored by control room or control room operator. Okay, now the tool they deploy for doing this is PPCS or Basic Process Control System. Commonly you call it as distributed control system or your control panel or whatever you call it. Okay, or your PLC. Now, basic process control system, what it's doing, it is continuously monitoring the process where the actual parameters should be there. Suppose you are wanting to keep the pressure at say 10 bar, then it will keep on ensuring that monitoring by some pressure sensor or something that all the time the pressure remains at 10 bar or around that, maybe 9.8 bar to 10.2 bar. That kind of variation is tolerable. And the moment it tries to go beyond 10.2 bar, the process PPCS system, it will regulate the system back to 10 bar level. Okay, 10 bar pressure. Okay, that is the way the PPCS operates. It's a modulating control, regulatory control. Okay, and suppose despite its best intention, suppose the PPCS is not able to control it and it goes beyond 10.2, which is the set point, then what will happen? An alarm will come. Okay, the alarm and operator action needs to be happening here. Okay, the alarm will initiate action from the operator who will take some action in the plant processes so that the things will process will come back to the control region. Okay. Now this is a necessarily a manual intervention would be required here. But is it always preferable to have depend on the manual intervention? Not necessarily, isn't it? You would ideally like the process control to take care of itself, but it is not always possible. And the alarm comes, and sometimes the operator is not able to take action because he is busy somewhere else, or he forgets, or he ignores, or whatever it is. In that case, if the deviation which is caused by something not normal, then it may go further deviate and ultimately you may pass on to the high temperature limit also or high pressure limit also. At that time, you cannot allow any further deviation. So what you have to do? There you install a safety instrumented system or safety instrumented function. What it will do? It will just shut down the plant. It will not allow the deviation to proceed further. It will shut down the plant and ensure that you are not encountering a dangerous situation. So it does not regulate like the basic process control system. It just shut down. It has only two positions. Either it allows the plant to operate within that given time process pressure range or temperature range, or it shuts down the moment it crosses that limit, high limit it crosses, it will shut down the. Okay. Now beyond this safety instrumented system also, there are some more layers. Okay. See, sometimes everything in real life, you can see everything is likely to fail. Okay. That means today you have installed a best possible safety system, but it can also fail. So in order to take care of that, there are some additional seven layers are given in the layers of protection concept. These layers of protections are typically relief wall, rupture disk, and defensive systems. Okay, these will suppose the safety instrument function phase to operate or phase to protect. These layers, which are mitigative layers. See, our safety instrumented function, what it is doing? It is preventing the accident to happen. Okay, before the accident happens, it is preventing it. But relief valve, rupture disk, and FNG system, these are mitigative actions. That means what they will do. Suppose there is a large pressure variation, then you will relief valve will relieve the pressure inside the particular vessel to a safe place and take care that the explosion does not happen. Or the rupture disk also can take similar action. FNG system will what they will do, they will start the sprinkler or reduce the fire size or something. Okay. So these are all mitigating measures. Please understand the difference between a mitigating layer and preventive layer. Safety instrumented systems are preventive layer, relief systems are mitigative layer. Then subsequent to that, there could be other layers. See, up to now, whatever layers we have seen, they are somewhere or other actively participating. Okay. Now, embankments like dike walls around the tank, they are what they are doing. They are just not allowing. Suppose there is a spillover from a tank. What this embankment layer does it prevent anything? Does it mitigate anything? It doesn't mitigate anything. It only limits the that whatever is the spilled thing, maybe acid or some volatile substance or maybe some hazardous substance, it will not allow to travel all over the plant, but it limits it within a given area, which is the dike area of the particular tank. And lastly, the last layer of protection is plant emergency response. It could be many things. It can start from evacuation. It can go to fire, calling a fire tender, or and many things are there. Something which may be outside the plant also. Okay, asking the community nearby to vacate. So many things. These are all emergency. So these are the seven layers of protection, and these are explained like this. And we are using these seven layers of protection in the process design as well as the implementation of the running of the plant. Okay. Next slide, please. So process plant design is unique for each project, and depending upon the final product a company has to produce, it progresses through multiple stages of technology selection, basic engineering, detailing, etc. In process design, we use various standards and guidelines, including corporate guidelines. In plant process design, we use many standards like API standards, NFPA standards, ATEX directive, etc. To name it. When we say the process design is robust, it means that the multiple layers of protection is used in the process design to make it safe. Okay. Next one. Process design and the role of regulatory bodies. As mentioned in the previous slide, the role of robust process design was explained. But when you are implementing a large oil and gas project or petrochemical chemical plant, it is impractical to think that the corporate body which is implementing the project on their own will follow the good engineering practices and Indian or international design standards to ensure safety. Therefore, every country needs a regulatory body which has to ensure that a plant design is safe. Therefore, critical documents are subjected to approval from regulatory bodies. Okay, next slide, please. Now, role of insurance company, large oil and gas plants or petrochemical plants, despite the best design practices, are having some risk of accident. Even a small accident may cause disruption in production, loss of an asset, environmental loss, or injury or fatality of human being. Because of the strict regulatory norms, such accidents cost very heavily. Okay, you have to pay compensation, you have to pay. Suppose the asset is lost, then you have to recreate that asset or maybe import a machine or maybe import a probably a compressor station or something like that. Okay, so because of strict regulatory norms, such accidents cost very heavily. Then the plant owner would like to buy insurance cover for the against accident. The insurance agency in most of the advanced countries to read studies before declaring insurance premium. The insurance premium gets rebate if all the safety studies are done and regulatory norms are followed. Okay, declare. Now, let us take a break here.
Yeah.
Shalini, are you there?
Hello.
Shalini ji, yeah.
Shalini, you can,
Hello.
we are taking a break for 10 minutes. Okay.
Yeah.
So, question number 1 and 2 you can take.
Yeah, yeah.
Okay.
Okay, I will just put these one and two question.
Polling, yeah.
Yeah, for polling.
Yeah.
Uh,
Okay, sir.
Yeah, yeah.
There are three answers given here. Question. So after the part one, question number one becomes applicable. Okay.
Yeah, yeah.
Okay.
Okay, okay.
We are taking a break for 5 minutes.
Okay, okay, sir. No issue.
10 minutes. Yeah. this polling session. Now, the answer of the first question: what is concept of layers of protection? As sir explained in previous slide, the answer is one. That is the 1 minute. It is structured process to add multiple barriers between hazard and consequence so that risk can be reduced. The sir explained in that risk concept slide that there is acceptable and unacceptable risk. The gap between that we need to come as close to the acceptable risk. So by adding layers of protection, we can do that. Okay. So answer is one. Now the second question was, what is role of regulatory bodies in functional safety regime implementation? So that also the answer is one, to ensure before allowing to permit installation, permission, major modification in a chemical, petrochemical, oil and gas facility, that all safety studies are completed and the risk to environment, personal assets due to operation of plant facilities within limits as per the national standards. Okay. Then only the regulatory bodies would waive off the premium and these things. Okay. So if you all are comfortable, then we can start our next session, means next slide, part 2. Okay.
Please raise thumbs.
Please raise the, yeah. Okay. Thank you.
Okay, part 2, functional safety basics.
Yeah, part 2, functional safety basics.
Life cycle concepts of IEC 61508 and IEC 61508. I explained to you that IEC 61508 and IEC 61511 are very important for the functional safety industry and for the process industry. So it has to be, and functional safety, as I told you, is based on reliability science. Okay. We will learn as we go by, we will learn about how numerically it is explained. Okay. But basically, you can achieve such high reliability only when you have a structure around it. Okay. See, if you allow things to just happen by itself, you can never probably ensure that when it has to operate, it will operate. Okay. But if you all the time meticulously monitoring something, closely guarding something, then only that entire life cycle, if you are covering, then probably most of the times you will be able to get the response from the safety system the way you want it. Okay. So we first of all please understand that functional safety is an offshoot of reliability science. What is reliability? Once you design and implement a reliability system, it will every time behave exactly as it was designed and implemented. In functional safety, we have a reliable system which always performs as it was expected to perform. Next. So in part 1, we understood risk concepts. We decide how much risk is acceptable to our company and express it numerically as a benchmark in our risk matrix. Every company has a risk matrix. We'll down the line we'll learn about risk matrix, but at the moment just take it for granted that your company, wherever you are working, also will have a risk matrix, and you can express in that particular risk matrix numerically how much is acceptable to you. Your corporate guideline gives you that. Okay. So when we conduct hazard and risk analysis, HRA typically what you call it, hazard and risk analysis of your plant process design in a hazard station using the corporate risk matrix, wherever the risk is beyond the tolerable exposure risk, we need to reduce it so that hazard does not get converted into consequence. Okay. What is consequence? Consequence is an accident which you do not want to have. The Piper Alpha incident, Occidental was the company which was operating that plant, did they want that accident to happen? Of course not. They didn't want that explosion to culminate into a huge catastrophe and 167 people died. That was not their intention at all. But something went wrong down the line, and now since we have this safety system, functional safety standards, things can be controlled in such a way that hazard does not get converted into a consequence. This is achieved by introducing layers of protection between hazard and consequence to reduce the risk. As some time ago, graphically, we show how to introduce these various layers of protection. All these layers of protection must be reliable and always must provide reliable performance. And when called upon to act, please see the Swiss cheese diagram on next slide to understand this concept. Next to the slide. Or is this them? Yeah, this is the Swiss cheese diagram. See, typically these layers are shown. You all of you must have seen this cheese. Okay, the cheese which you buy from market, and if you slice it like this, you will find that there are various holes into the various layers. And suppose you there are four slices of the cheese you take, and hazard is at the one end, and finally travels through all these layers. Okay, and if for some reason all these poles are aligned, what will happen? Hazard will become a consequence. Okay. So these are various layers, and these layers are things like engineering controls, administrative controls, behavior controls, mitigation barriers, weaknesses, and these poles are nothing but weaknesses. So this, if the hazard is passing through all these weaknesses, then the consequence is going to happen. Obviously. Next. Now, three types of failures are recognized in IEC 615. Okay. Now, what is happening is these various failures which can happen in actual working of a safety system that we have to address. Okay, we showed in the Swiss cheese diagram that there are inherent some weaknesses. Although your intention is to have a very fail-safe system, a robust system, still there are some weaknesses, and if these all the weaknesses get aligned, then your hazard can become a constant. Okay, so still compliance means that the three actually the reliability science identified in functional safety that these weaknesses which we showed here in the system diagram, they are nothing but three types of failures. And what are these three types of failures? We will study that. But first of all, please understand that if you control these three types of failures, then you are able to perfectly control these layers and ensure that the safety layer or the safety system works exactly the way you want it. Okay. So what are these three types of failures IC standard acknowledges? The answer is there are three types of failures the IC 615 and understand. These are random failures, common cause failures, and systematic failures. I will briefly see the explanation to this is this can take about 1 hour also, but we do not have that much time for our session today. So I will quickly cover it, but I will explain the concept in more generic form so that you get at home with this. Okay. A random failure is typically any failure which happens because of fatigue or usage can't be exactly predicted, but failure can be established by testing and simulated calculation. Okay. Now, yeah, to just show what are random failures, I will show you one slide. First, we will pull up. Okay.
Thank you.
आगे
हो गया.
अरे यार
Okay. ठीक है,
ठीक है सर।
एक मिनट वो खोलिए ना।
मैं बोल
हाँ, मैं करता हूँ।
जस्ट अ मिनट।
Yeah. So, only a second. One minute. Yeah, 1 minute. I will share my screen for that diagram. Yeah. Can you see my screen? Everyone, just show your thumb. Okay. Yeah.
Yes, it
Can
is
you
visible.
see?
Uh,
Yes, sir, it is visible.
So are we sharing it?
yeah.
Nobody is raising thumbs.
No. वो दिखेगा.
Yes,
Yeah.
they are raising
Okay.
thumbs.
Okay.
Yeah. Okay.
Okay. So this curve is called the path term curve. Okay. And what you can see on the x-axis is the time, and on the y-axis the failure rate. Okay. So if you say any device which you are using in a family system, it can fail randomly. Okay. Any device can fail randomly. Suppose it's a sensor, say transmitter. The transmitter can fail randomly. That means it can fail any time. Okay. But the study shows that the failure at the initial stage, that means suppose I develop a transmitter, manufacture a transmitter and then launch it in the market, then initial maybe some 2 months, 3 months, 6 months period, it is likely to fail quite often and it is called infant mortality period. Okay. Then at the end of the life, suppose if the transmitter has got a 10 years life, then again at the end of life, again it can frequency fail. But in between, we have a time which is shown here,
Yeah.
which is shown here.
Yeah. 1 minute. This see my arrow. This one. Normal life it is.
This is normal life. This is the period when it is, this is the useful life they call it. And in this period, the failures are quite, you can say, standard. Okay. That means the number of failures will be
Yeah.
typically would be standard, maybe one failure per year or one failure per month. Some kind of you can establish the failure rate.
Yeah.
So this is we are most interested in, and most of the devices when they are used in the functional safety, they are practically used in this
Useful life.
Okay.
Useful life it is given.
Go back.
Okay. Shalini, you can share your screen now.
Okay, sir, I'm sharing.
Yeah.
Okay, just move it. You can.
Sir, you can take control.
Yeah. Okay. Yeah. One minute.
Yeah.
Okay.
So random failure is, and it could be because of various reasons. It could be because of the capacitor may fail because of a maybe some electrolyte has just evaporated or something. Okay, so it can happen. Now, second type of failure is common cause failure. That means a particular failure can happen because of some indirect causes. Suppose you are using, I'm just giving a practical example to understand. Suppose you are using a transmitter to measure level of a tank, and process guys said that no, 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 only one transmitter if you use. If that fails, then how will come to know the level? So you decided to go for redundancy. Okay. So instead of one transmitter, we use two transmitters. But unfortunately, what the construction guy did, he just used the same tapping point and took two connections from that and connected it to the transmitter. So now, because the tapping point is common, if some kind of debris blocks the tapping point, what will happen? Although you are having a redundancy, both the transmitters will not be able to read the level because the common point, the common junction of where from you are taking the signal, that itself is blocked. So this is called common cause. And there are many examples like this. Suppose a plant is there where you have a duplicated sensor, but suppose power supply goes up for all the three instruments, then although you are having multiple channels, you are not able to get this. Or a fire happens, or a some catastrophe happens, which is common to all the sensors. Then this kind of thing is called common cause. And most of the times it is because of some kind of environmental disaster or things like that. Okay. And the third type of failure is most important. The third type of failure is systematic failure. That means what? That means system, with the system something has gone wrong. Okay. What is system? System means you are talking about functional safety system. Okay. So either during the manufacturing or during calibration or during commissioning or during design or during maintenance, throughout the life cycle, somewhere you did some mistake and that is causing the failure. Now, because you want a reliable system designed as per IEC 61508, to be working available all the time. So can you afford this kind of systematic failure? Of course not. So you must design every phase of the life has to be under a proper regime which will ensure that this failure is tolerated or it will not affect the final behavior of the instrument, okay, or the particular system. Next slide. Now,
Yeah,
this is all.
this is the explanation and this is already done. Yeah.
Okay. Now we have been talking about SIL compliance and this various things. Now let us understand. See, anything you say, you must have some kind of measure. So here, for SIL compliance, the standard gives a measure called safety integrity level. Okay, and it is shown here by a table. Okay, an example, as explained in the previous slide, since compliant layer protection is most reliable, but first understand full form of SIL. It is a safety integrity level. There are degrees of SIL level as shown below in a simplified SIL table. This is little bit simplified. This is not the IEC 6150 table, but for the sake of explanation, we have removed some plus greater to less than signs and all, but just to make the concept understood. Okay, so there are four levels of SIL: SIL 1, SIL 2, SIL 3, and SIL 4. Okay, and what are so this table in entirety explains this. So and this is a very popular table. So most of the people who are working in functional safety, this table is by heart to them. Okay. Anytime you wake them up even from sleep, they will tell you, okay, SIL 1 is this, SIL 2 is this, SIL 3 is this. Okay. So this is the SIL table. Let me explain you one by one. So first column of this SIL table is SIL 1, SIL 2, SIL 3, and SIL 4. SIL 4 is shown in red color because normally you should never encounter it. SIL 4 is very, very, very high risk. Okay. And one should not enter that arena at all. Okay. Normally, you should restrict your plans to SIL 3. Okay. Let us understand what is SIL 1, what is SIL 2, and what is SIL 3. First, we have to understand a term called PFD average. PFD is what? Probability of failure on demand. Okay. See, I have been telling you that SIL is based on reliability. Okay. So probability of failure on demand means what? That when you a demand, actual demand on that particular reliable system comes, you expect it to be working, available. But if it is not working, then what? Probability of failure on demand explains you how many times it will be found failed when actual demand comes. That means when if you are measuring a particular level, that level is very critical for your operation, and you want to know that when the level reaches that point, you must be intimated, okay, or some action must be taken. And at that time, suppose your device is not functional, what will happen? It will not be functioning. It will not be giving you the required result. Okay. So this is the failure probability which will be likely in the lifetime of that particular thing. Okay. So this is expressed numerically. Okay. Now the next column is safety availability. Now something if it is not available, which is expressed by PFD average, then how you will calculate availability? Just subtract it from the PFD average from 1. So the safety availability 1 minus PFD average. So you can see column number 3 is nothing but subtraction of column number 2 from 1. So you get this type of figures 0.09, 0.099 and all that. Okay. And now you can all understand one thing that PFD average is very good, safety availability is very good, but for a common human mind, people are less uh, understanding this point 0.1, point 0.01. These are not very much readily accepted by human mind. Okay. People are more likely to accept integers or digital things like 10, 100, 20, 30. Full numbers they more prefer. So risk reduction factor is a term which is nothing but a reciprocal of PFD average. Okay. So that is easy to understand. It is same thing expressed but just by reciprocal function. That means if you want to express PFD average of 0.1 to 0.01, you can express it risk reduction factor of anything between 10 and 100. Okay. This is the explanation given for this cell table. Okay. Everybody understood? Please raise your thumbs if you understood.
Okay, we move. Yeah.
Thank you. Now, basic explanation of the table I already have given you.
Yeah.
The table is easy to understand, but all these things I have given to you. You just read it once and
We will move on.
yeah, we move on.
It is, yeah, it is like 1 in 10 years, 1 in 10 times, 1 in 100 times like that failure. Okay. So that thing
There
here,
are no units to this.
there are no units. Yeah. So here it is explained.
Okay, next slide.
Okay. We can move forward. Yeah.
Now, this is the life cycle concept. Okay. Probably again you have to share that.
Yeah. 1 minute. I will share that. थोड़ा बड़ा नहीं. This is 508.
Okay.
Okay.
So,
This is the IC
6150 table.
Yeah.
Okay. See, I have already explained you the importance of IC 6150 and IC 6151. Okay, what is the distinction between them? Now, here is the complete life cycle. As I have explained to you, unless you, at each and every step, you monitor the life cycle, you will not end up with a reliable product or reliable system. That's why this is very essential that and the standard mandates that the entire life cycle must be completely under control. Okay, how you can do it? By following exactly this way. Suppose you are a manufacturer, so you start with, suppose you are manufacturing a particular transmitter. So you start with a concept. That means probably you are going to use a particular sensor, type, which maybe a strain sensor or some induction type of sensor. Then you will have a D2A converter, A to B converter, whatever it is. Okay. So this is the conceptual discussion. Then once you understand the concept, what you will do, you will overall scope definition. You will do that. Okay, I will have sensor from Motorola or some such company. Then hazard and risk you carry out. Two, three things you compare, then you find that Motorola is very good for some other one is when the negative exit fails. So you hazard and risk analysis you carry out. Then next thing, what you call overall safety requirements. So that means suppose you find that those strain gauge type of sensor what you have selected, that whether it is all the requirements, that means whether minus temperature or plus temperature, whether everything it is able to take care. So that kind of other this kind of overall safety requirements that it can be done. And then you see overall planning. Once you for doing all this entire life cycle, lot of planning is required. That somebody has to put together all the steps in the design. He has to put together. Then he has to overall safety evaluation planning. He has to do overall installation commissioning. All this planning needs to be done. Then various installation commissioning type of thing. Then safety related system. Various steps you have to closely monitor, and all these three steps are monitored by a vertical bar which is shown here, functional safety management. Okay, and because you want everything to be perfect, then it can be perfect only when you have proper documentation. Okay, so reliable things can be produced only when you have a functional safety management and a documentation. All these steps of the manufacturing developing are monitored correctly. And after that, after your everything is done, what you must do? You must do verification. That means whatever you have done, whether it is the software or hardware or whatever design you have done, that must be verified. And finally, functional safety assessment. The moment somebody does the verification, somebody must check that he has correctly done it. Okay. So these are the various steps in a safety life cycle of a 61508 life cycle. Okay.
Now the sir explained you three types of failures. In that, systematic failure, which is most critical, for that the step here, functional safety management, it is most important and key role in this. And in this life cycle, one more thing is important, that is safety requirements,
Safety requirements
specifications, which generally is provided by the user.
we are going to learn about it.
Yeah. Okay. So we move to another table, that is IC 6151.
IEC 615 is identical to IEC 615.
Yeah.
Only thing what they have done, for convenience sake, they have combined certain stages and come up with a
Overall
life cycle which is consisting of 8 steps. In IEC 6150, it is 16 steps. Here it is 8 steps because some of the steps are combined. Okay.
Yeah. Shalini, you can share now.
Just me?
Yes, yes, I'm sharing.
Hello?
Yes, I'm sharing.
Yeah.
Yes, you. So you can take control now.
Yeah. Yeah. So life cycle concept explained. Here we explained the functional safety standard. We also explained hazard and risk and requirement of reliable functional safety system based layer of protection. But the life cycle concept means a lot more than just to provide in design a functional safety layer, but ensure that there is an ongoing mechanism which from concept to commissioning and during operations of plant life cycle ensures that seal compliant system provided as a layer of protection remains maintained seal compliant and provides the same degree of protection or risk reduction throughout the life cycle of the plant, typically 15 to 20 years. Okay, so that life cycle concept ensures that whatever seal compliant system you have implemented remains as it is for typically when you are running your plant. Okay, so for that, that is very much important. We move to next slide.
Yeah. Now, functional safety management, the maintaining of the safety storage system to provide same degree of risk reduction from target to grave is an onerous task and it can be achieved only by functional safety management using life cycle concept. The life cycle demonstrates the method to ensure compliance throughout the entire life cycle. If an organization ensures that not only they are practicing functional safety management concept by meticulously following the life cycle, it is able to meet the documentation compliance requirements of the respective IEC standard, either 6150 or 615, whichever is applicable, then that organization could obtain a FSM compliance certificate. This is very important. See, just by leaving it, self-certification in functional safety management is not possible. Okay. Some third party, knowledgeable third party must audit your, suppose you are a manufacturer, then your all manufacturing steps will be audited by a third party. And once you find that they are meeting the requirements of the standard, then they would certify what? Compliance of the certification money. That means your systems are compliant to the certification required. That is what the third party or auditor will certify. And as you can see in case of IC 6158, every state you have to demonstrate compliance, while in case of IC 6151, the standard gives you concession to combine two or three stages together. See what happens in IC 6151 typically, why this concession is given is because IC 6150 is very much within one manufacturer, within one house of a manufacturer company. But IC 6150 deals with users, system integrators, operators who are different entities. So something which is in the operator's devices, the system integrator may not be able to control. That's why 6151 standard gives some stages can be combined. That means the end user can outsource the maintenance of a particular system to the system integrator who integrated it together. So subsequently to the rest of the life cycle of that particular plant also, the same system integrator can make an annual maintenance contract and continue to maintain. Okay, so that kind of thing is possible in case of functions of management. But in that case, that system integrator has to be FSM compliant. Like it should be certified by a third party auditor like TV or Synology or things like that, which will give them a functional safety certificate. Okay,
Yeah.
next week. So here we are coming to end of part two. Shalini, huh?
Yeah. So we have come end of part two. So Shalini ma'am, you can these are the questions, two questions. You can raise the polls, okay? And we will give you 5 minutes, okay? You answer that polls. is C1 is 10, C2 is 100,000. Yeah, so Shalini, we will close the polling, okay?
Oh, okay. I'm just close.
Yeah, close that. Yeah, I will explain. Yeah, okay.
Yes, now polls are closed. You can explain.
Yeah, so first question was, is functional safety life cycle identical for IC 61508 and IC 61511? So, as sir explained, IC 61508 is an umbrella standard, and from that, IC 61511 and all other standards are provided as per the various industries. Okay, so yeah, for this one, the answer is one. That is, no, IC 61508 has 16 phases, while IC 61511 has around eight phases. Okay, so there are number of phases in 61511 is less, as the other phases are combined in IC 61511. Okay. Now for question 2, C2 safety instrumented function will provide how much risk reduction factor. So in that there were three options. So first option was to confuse you all, that is from 0 to 100. Now C2 system has a risk reduction factor of 100 to 1000. Okay, that is PFD average of 0.01 to 0.001, and availability will be safety availability will be 1 minus of that PFD average. Okay, so shall we move to part 3? Just show your thumbs.
Which is so part three is assessment technique. So what did we tell you in the initial first lesson, first part? We told you about risk. Okay, risk concept. Now the risk concept we also told you that every organization will or corporate guideline will be there for risk matrix. Okay, so and we talked about this being a subjective issue. Okay, something which every corporate or every country or every region can particularly decide whether a particular risk is okay for you or not. Okay, and then based on that guideline, you first decide what is uh, tolerable to you, and then try to assess the existing risk in your plan for each type of hazard which is likely to become a consequence. And once you find that it is uh, within your tolerable limit, then you don't have to do anything. If it is beyond your tolerable limit, you have to use some kind of safeguard so that you can reduce the existing risk to your acceptable risk norm. And if it is goes beyond, much beyond your acceptable risk, then you have to do some kind of risk assessment study technique. You have to use some risk assessment study technique and then decide your existing risk. And according to the assessed risk, you have to bring it down to your acceptable limit by putting in some safeguards. And what value of still is there, safety indicator level is required to bring it to your existing acceptable response is decided by using certain techniques like LOPA and things like that. So that, or there are some qualitative techniques also, which decide how much risk you can reduce by using certain risk reduction techniques. Okay. So let us first understand what is the risk matrix. Okay, risk matrix and its application. So a typical 5 by 6 risk matrix is shown here. Okay, and here as you can see the colorful diagram at the left side, you can see that the two important risk related things which I told you in the morning, consequence and frequency. Okay, so consequence is shown here on the x-axis and frequency shown on the y-axis. Okay, so here now to make it see just by frequency and consequence you do not understand how to calibrate it. That kind of thing you do not understand. First of all, what are the various risks? Let us understand that. Okay, a risk to a in a plant can be defined as it could be a risk to people, or it could be a risk to asset, or it could be a risk to environment, or a risk to the reputation of that company. See, it is in order to make this discussion more understandable, let us see in each case these risk receptors, what we call as risk receptors. That means if the risk gets converted into a consequence, if the hazard gets converted into a consequence, how you are going to, what is going to happen? Whether it will, what is going to be the likely risk receptor? Whether it is going to be some people or some asset or some kind of environment incident it is going to be, or some kind of reputation kind of consequence it is going to be. Okay. So in each cases there is a risk matches gives you a method to understand uh, to calibrate some kind of calibration. Okay, that and then once you calibrate it, then you can sort of address it appropriately. Okay, so let me explain in detail. For risk sectors, people means what will happen if this severity is very high, then some people may die. More than one person may die. In that case, there is severity is five category here as shown here.
Yeah.
There is category shown here. Yeah, five category risk will be there. Then it will be some kind of very high risk.
Yeah.
Minimum three in this particular corporate, they say that the corporate guideline is that when three people are more in danger of fatalities are likely, then they call it a five category risk. If there is some kind of risk which is up to three fatalities, then it is four category. If something major injury is going to happen to multiple people or some people, then it is a three category risk. Minor injury if it is there, categories risk categories two, and slight injury is category one, and no injury that is everything is safe. So no injuries or no health happen. So this is in case of people we are explaining it this way, expressing it this way. Same thing can be for assets also. The consequence can be asset damage also. So if there is no damage, we consider it that zero damage, that means no damage to asset, and this is an acceptable situation. Now, slight damage. Maybe every corporate has got a number for this. In India, we term it in number of rupees. They would say up to some a big organization like say Reliance Industries. They may say that anything say up to 100,000 rupees is a slight damage. Okay. While it's category two asset damage, they would define it as 1 million rupees. Okay. Or a category three thing they can say that 10 million rupees. Or category four could be 100 million rupees, and category five could be maybe 1,000 million rupees, something like that. Okay. So this is the way you calibrate your risk matrix. And then in case of environment also you can calibrate it like this. So if there is no damage to the environment at all, that means there is no envelope broken anywhere, no effluent going out anywhere. So it is a no damage type of thing. But if it is a very high damage, probably the hazardous leak happened from your plant and it entered into the nearby community, and probably some fatalities outside your plant also happened. That is a very, very severe environmental damage, or probably the you polluted one huge lake of water which is adjacent to your plant. That kind of is a very huge environmental damage. And lastly, the reputation. See, when a company is operating in an environment, it gives employment to people, it gives taxes to the government, and so many good things it does for the society around it. But same way, if there is a major accident in a company, what will happen? That accident news will appear in the local newspaper. If it is only limited to local newspaper, then it could be defined as a slight impact. But if it is coming into the radio news also, then it is probably something higher. Then if it is coming in the TV news also, it is something much more. And if it is coming in the national media, it is the worst kind of thing. So this kind of reputation damages, people probably will not join that company, or punitive measures by government of that particular country can be taken. So this kind of calibration of the consequences is done here. And same thing easily for the frequency is done like this that never heard of this disease. That means this is a very, very rare occasion. Heard in the industry that this is slightly once in a way probably in the industry for happen somewhere. Has happened in the organization. Suppose you are in a particular company. That company itself, suppose in some other plant, maybe in Odisha or maybe in Punjab somewhere down the line it has happened, then it is considered that this is a C category consequence, likelihood. And something has happened in the location. Like suppose in the plant where we are deciding this, there itself it has happened that it is a D category. And D category is that it has happened many times
in a year,
past out
location in a
things like that. And it is by simply showing it by color, you can see the severity. So the red type of band is never enter.
Yeah.
The yellow type of band is once in a while the expression may be permitted, so probably with some engineering controls about this to controls and all. And blue is the region where normally you would like to live with. Okay. So this is the kind of
Yeah.
calibration of the risk matrix, and every company should normally be having this risk matrix for its plant operation. And the examples are given here. I've elaborately explained here to give you a feel of the
Yeah.
what kind of risk
So-
matrix is there.
So basically, if say the consequence has occurred, and it is the people means no injury or help to the people, then asset is no damage, no effect, no impact, and the frequency is that it has happened in organization once in a year, so it will come like multiplication. It is a blue color here. Okay. Similarly, for yellow here, it has occurred more than once a year in an organization, and if people minor injury is there or minor damage to the assets are been occurred or minor effect to environment is there, so this is yellow. Like that, we will means calibrate it. Okay.
Based on the risk sector, risk sector, as I told you, there are four types of risk sectors: people, asset, environment, and reputation. So, based on which particular risk sector is getting affected and to what degree, that is calibrated like this, and this is available for you for your risk analysis and risk reduction.
Yeah.
Okay. Next slide. Now, HAZOP is a structured and critical examination process, and by HAZOP you can actually your process design part of your uh, plant, you can take it and do the structured analysis as of session. You can do it, and by doing that, you decide how much risk and what kind of risk is there, and which type of risk you can analyze and see which risk sector is getting affected and what kind of consequences there. Okay, but typically there are many misconceptions about HAZOP. Many people think that it is for equipment you can do a HAZOP. Typically, it is not meant for an equipment. Okay, for equipment you can do some other type of studies like FMEA can do. Okay, but for HAZOP, typically it is applicable for a particular plant. Okay. So here structured critical examination, the representative thing which is taken is the P&ID, process and piping and instrument diagram or process and instrument diagram, whatever they call it, that is taken as a starting point, and the based on that, because every when you are doing the process design, your ultimate deliverable is the two things. One is the process data sheet, and second is the P&ID, which are very structured documents. And once you go through the P&ID, represents the entire plant in a very systematic way. So there, if you carry out a detailed HAZOP, you are able to see what kind of consequences are likely and when it can happen, what is the likelihood, what is the consequence, Once you know both the consequences and likelihood, then you can calculate the risk. Okay, this is the way we structured analysis, and as per Indian standard for international standard for HAZOP is IEC 6182, and based on that it is carried out. Okay, and it is a team exercise. Okay, all possible deviations from the design intent are examined. First of all, please understand what is the design intent. Design intent means that what that particular, suppose there is a particular vessel, at the inlet of that particular vessel, suppose you want the, as per the design intent, you want it to be a flow rate coming in that vessel at some particular liters per minute, then that is the design intent. Pressure of that particular fluid, whatever it is coming, you want it to be some degree, some uh, bars or some the temperature would be some degrees centigrade now. So that is the design intent. So all possible deviations, like I mentioned, three things, that is pressure, temperature, and flow rate. So in the design stage, somebody has designed that particular vessel for a particular flow rate, particular pressure rating, and a particular temperature. So if any of these design intents are violated, then it will be considered as a hazard. Okay, that the hazard is evident that because your design intention is say 5 bars, but you are likely to extend to into five from instead of five, it is going to be zero point 0.5 more or 5.5 or 6 or something. Then it is a deviation from the design. Okay, so this is the design intent is to be examined in case of a law, and because that design deviation has taken place, if that deviation causes a consequence, the consequence of the undesirable effects are examined. That means the increase from 5 to 5.5, whether it is going to damage the vessel in any way, whether it is likely to rupture the vessel, whatever be the consequence that is examined, and adequacy of safeguarding
So SS.
asset. That means whether it is properly designed as per the code and codes and standard, and whether it can withstand this additional pressure rating or temperature rating or temperature pressure rating. Okay, that is carried out in the HAZOP in a very structured. Okay.
Yeah, so typical HAZOP steps, as sir said that it is HAZOP is done as per standard international standard IEC 61882 and BIS 15656. Okay, so typical steps to conduct an HAZOP study. Basically, first we need to define a scope of project, determine study nodes, means whatever PNIDs are there, we need to mark up the different nodes in that PNID, and one by one that node has to be evaluated for the design intent. Then once that has been done, then apply the guide words like no pressure, less pressure, high pressure, no flow, less flow, reverse flow, misdirected flow, high temperature, low temperature, like that. You need to apply the guide words to study each node, then determine causes and brainstorm the consequences. Each cause has to be determined, and what will be the consequences if that cause happens. That needs to be brainstormed with all of the bunch of the team members, and then after that brainstorming, you need to identify the safeguards. Which are the safeguards to, if that consequence happens, will take care adequacy, and then if there needs there is a need to provide some recommendations, then you need to write down the recommendations that please involve this step in a maintenance procedure or in your procedure or in your protocol, day-to-day protocols, some administrative measures. Yeah. And lastly, you need to document the results, like final this HAZOP recommendation report, and all this has to be given to the client. Okay, so these are the typical HAZOP steps to be considered during HAZOP study. Next slide. Yeah.
So these are some of the important things which must be defined. And a node is a these are typical terminology used in a HAZOP session. Node, design intake, deviation, qualification, safeguard. Okay, let us define all of this. Node is a specific location in the process in which the deviation of the design process intents are evaluated. Okay, that means it's a segmented area. Suppose in the P&ID, suppose there are some 10 equipments are shown and about 20 pipelines are shown, process lines, and we are seeing from left to right, then you would like that we would restrict this uh, node to out of 10, maybe 3 or 4 equipments you cover, and then mark it with a colored highlighter, okay, and you segment that particular one, and segment that particular one and mark it up so that people will be able to identify that node as with some number, node 1, node 2, node 3, whatever it is. Okay. And then once you mark it up, your discussion of the team will be limited to that node only. That means you are not, when you are discussing that node, you will see all connected pipelines, all connected vessels, all connect design deviation and design intent, all you will be verifying with respect to that particular node. So design intent is the description of the how the process is expected to behave at that node. Suppose it is flow is going to happen from left to right, and suppose for some reason it happens from right to left, then it's a deviation. But design intent is that the flow should happen from point A to point B, okay, and it should be happening at one particular pressure or temperature or whatever it is. And deviation is a way in which the process condition may differ from the design of process system. That means it could be pressure going high, low, temperature going high, low, or flow not happening at all. This also could be a deviation, or it could be any other deviation like level going high, high, or level going low, low. Okay. So these kind of deviations are common in process design, which are particularly discussed during the HADOP session. Now, because of this deviation from design intent, what could be the consequence? The result of the deviation, in case it occurs, it may comprise both process hazards and operability problems, like plant shutdown or off-spec power issue. Suppose sometimes there may not be a real process consequence like vessel getting ruptured or temperature going very high or something. But end product after that particular step, suppose it was supposed to be some color, say yellow color, and it happens when you find the final product is coming out, which is not yellow but green, then you would not like that. That's the contamination of the product. So you would not like that product to be of deviating in the color. So you will take appropriate action. Maybe that is a quality problem or some quality issue is there. So consequence can be of very severe or severe from the point of view of people or from point of view of quality of the product. Okay. Then safeguards are facilities that help to reduce the occurrence frequency of the deviation or to mitigate that consequence. These include, for example, alarms, automatic control systems in place. The alarms will always tell you that something has deviated. Suppose the temperature alarm is there, it will tell either the temperature is going up or temperature is going down below the design intent, okay, or it is going very high or it is moving too fast, okay. All these kind of things you will come to know from the various consequences will show you. Then alarms will show you. And the operator normally will have to take some actions. With every alarm, there should be, it should not be in such case that there is an alarm nobody has to do anything. No, that kind of alarm is then useless. That is not required to be provided. Every alarm should have a consequential action from the operator, either acknowledgement or taking some action somewhere else by closing a wall or opening a wall or some kind of action needs to be taken by the operator or starting under pump or some kind of thing he has to do to ensure that the alarm goes away or it remains in the same place. Okay. So these are the definitions of some of the terms which we use in Hazam. Okay. Next one. Now, guide words. These discussions, what happens in the Hazaf session, are by using these guide words. Okay, and these are standard guide words, and by using these guide words, we can we can control the discussion of the entire Hazaf session. These are standard guide words. No, that means not or none, and typical example is meaning none of the design intake is achieved. More with quantitative increase in parameter, that means suppose the pressure is high pressure or high level, something like that, then less of the what you call less not lower. That means quantitative decrease of the parameter as well as in additional activity. Suppose you want the pump to say a particular level of pressure to go up. In addition to that, the leveling of the production, that is some as well as. Okay. Then part of that is only part of the design intake is achieved. That means suppose you want a design intake to be doing two things at a time and only one thing is happening at that time. So that is only part. The reverse is logical opposite of design intake. Like I gave you the example that flow should be from left to right, and now it is happening from right to left. Okay. And then finally, other than that is complete different. Like I mentioned, that the final product is in red in color, but it's coming out green in color. So that kind of various guide words are being used. And then other useful guide words are which are these are typically used in batch processes, whereas that is applicable for flow transfer. So then before after these are typically for batch processes, early late or faster slower. These are the some other guide words. And there are depending upon the process plant where you are carrying out the error, some other guide words are also quite common. Okay. Okay.
Yeah.
Now, these just guide words are useless. Okay. So guide words are useless without a parameter. So these guide words must be associated with the parameters. What are the parameters? Temperature, pressure, source, reactants, phase, etc. Okay. So these are the various parameters, and so guide word plus parameter together makes a deviation. Okay. So the deviation will be completely defined only when you have both of these things, guide word as well as a parameter. Okay. Next one. Now, typical examples of process deviation, guide word is low, parameter is low, so deviation is low flow. Guide word is low pressure, parameter is pressure, then deviation is high pressure. Guide word is as well as, and parameter is one phase, or deviation will be two phase. Okay. Then other than compression maintenance, these are typically some other uh, guide which can be deviations can be shown as example. Okay. Now, a typical node of a PNID is shown here. Please study this node, then I will explain what it is. And we will try to do a very small head-off of this very quickly, but we'll do only for this head-off. We will do a explanation as given in the note, and then we will explain how we will do the head-off for this very small node of a PNID. Just study this for 5 minutes, then I respond.
Yeah. So so
Okay, so
have you understood this?
I will explain for
Yeah.
everybody's understanding. Typically, this is one node shown here, okay, and the explanation given. They are saying that this is a two-phase separator. The two-phase separator means what? It could be anything. It could be
Yes.
oil and gas or steam and oil, water, anything. Okay. So the maximum upstream pressure is 200 bar. The vessel operating pressure downstream FCV1 is 70 bar and vessel design pressure is given as 100 bar. Now scenario is overhead PT2 failure. Okay. Uh, PCV2 how is shown. PCV2 is having a PT transmitter. Okay. PCV2 is, and because of that overhead PT2 failure, this wall has uh, shut down. Okay, shut off. Then leading to vessel pressurization above vessel examination and loss of containment. This is the scenario which is given. The question to the team is: do we have enough safeguard? If is the scenario acceptable? Okay. Now, for answering this, let us try to do a very quick hazard. Okay. Because this is not an interactive session, so I will explain a particular way the derivation is happening and how it, what kind of safeguard we have to add to this. We will see. Okay. But before I do that, I have to do one thing. I have to explain you the process of hydrox, what kind of team is to be put in place to do the hydrox. Let us just, we'll come back to this node. First, let me explain to you the how the hydrox is conducted. Next slide. Typically, the hydrox results are captured in a worksheet like this. Okay. The It has got 1, 2, 3, 4, 5 columns. Okay. First column is deviation. Second column is cause. Third column is consequence. Fourth column is safeguard. And fifth column is recommendation. Now, In our case, there is a very small node. So in that case, we will just study one particular deviation, and then we will see what is the cause and cause, what is the consequence, and these consequence we will rate. Okay.
Yeah.
We have studied about the risk
Risk
matrix.
matrix.
So that risk matrix we will use, and the team will rate the consequence, and whatever consequence is higher than whatever is acceptable to you, either severity or likelihood, then we rate it, and then if it is the team decides that this much severity of the risk is higher than the acceptable, then the team will recommend a additional safeguard. Okay, and that kind of thing discussion will be captured here in the recommendation. This is the typically worksheet of a team exercise of hazard. Okay. Now let us understand the work process. Next slide, please. These are the typical resources required from client side. Suppose there is a refinery, then that refinery guys will put this kind of resources available to the HAZOP chairman. Normally for HAZOP, the independent person is called in to conduct the handoff. Okay. Now, independent, knowledgeable person who has got sufficient experience, say 15 years, 20 years experience in process design, operations, or things like that, then he would be called. So these are the resources from the HAZOP consultant. The HAZOP facilitator, that is the chairman, is called either a chairman or a facilitator. Then he would have a secretary who will note down the in the worksheet whatever discussion has taken place, but not each and every discussion point he will note down. Whatever the HAZOP facilitator tells him that now you record this, that only part the HAZOP scribe will record. Okay. And deliverables of the HAZOP session would be a HAZOP report. Okay. Action report. Now, from the client side, the minimum team which should be available is a process engineer who knows the process, the way it works, the instrument engineer, who knows how the various controls are there, operations engineer who knows exactly how the plant is operated, and a safety engineer. Safety engineer to ensure that the plant, whatever practices are there, they are safe and they are followed in as of session. And wherever he finds that that particular way is not safe, he will be making it and about not allowing that particular decision. Okay. Then electrical and mechanical people, if they are required, they will be on call basis. That means only for a short duration they will be present in the particular session. Otherwise, they will not be participating in. When required, they will be called, and this session continues till all the P&ID of the plant are subject to HAZOP session. And once all these recommendations are accumulated, then this report, draft report is submitted to the client. The client may decide internally that some of the recommendations are not possible right now because some new changes are coming in the plant or which the facilitator is not aware of. So the client will give an explanation that out of say 20 recommendations of the chairman has given, two recommendations or three recommendations are not possible to implement because some few changes which are going to happen 1 month or 2 months or 6 months down the line are automatically taking care of that, or they are not possible to make. Okay, some kind of thing. And then majority of the HAZOP chairman's recommendations are whichever are possible to implement that are accepted, and then the when it is considered that action report is completed, only when the client submits a detailed philosophy of how he is going to implement and masters the specific documentation like P&ID or the layout or whatever the down the line documents are there from documentation related issue is there, then how they are going to do that completely discuss and documentation partner, then only that action report is issued, and then the entire as of is considered to be complete.
And one golden rule for HAZOP is that no double jeopardy scenarios shall be discussed. Means this, if this will happen and this will also happen.
Two hazards at a time, two consequences at a time will not be discussed, and one by one. And if the okay, as Apurva said, double jeopardy normally is not discussed. Suppose the client wants to discuss it, then there are special sessions, and in this particular today's session, we are not going to consider double jeopardy. We will restrict it to one single consequence at a time. Okay. Next slide. Let us go back to the our node. Okay. So here this is the particular node.
Yeah.
Now this will be taken up by the HAZOP chairman. Now, the job of the HAZOP chairman is to ask questions. Okay. Somebody has been the process operator and the process design engineer from the client side. He will initiate the discussion. He'll explain what is the design intent, and then the HAZOP chairman will ask many questions like if the pressure increases, what happens, or pressure decreases, what will happen. Like this, they will ask many questions. In our particular case, here the scenario what is given here is that PT2 has failed and the PCV2 is shut closed, and because of that, what is happening here is the pressure inside the vessel is even vessel is increasing, and now the team is going to the head of facilitator will ask the question, and the team will discuss the consequences, and depending upon the discussion, they will record the team discussion. Once the HAZOP chairman concludes that discussion, they will record in the worksheet. Okay, this is the procedure which will be followed in the particular session. Okay. So here the particular scenario is given that PT2 is failed and PCB2 has closed down, shut down, and because of that pressure is rising. Now the chairman asks the question whether this is acceptable, whether initially they will discuss without safeguard. That means they will not consider the existing safeguard in the P&ID. But then safeguard, they will discuss without safeguard, and once they come to a conclusion, then they will discuss again same scenario with the safeguard in position, and then finally they will rate the consequence, whether this consequence or likelihood worth to be considered, and if they find it is severe, either very severe or very likely, then they make a recommendation about the particular consequence of the likelihood.
Yeah.
Okay. Now let us go to the next slide. So after this recommendation, from today's workshop point of view, we will be doing in the after that we will be doing based on the recommendation. We'll make some recommendations because this can't be an interactive session. So during the lunch time, we'll make a case for typically giving you a recommendation, and then we'll discuss what kind of scenario whether it is going to be, and we will try to see whether that particular scenario recommendation is implementable, whether it is severity, what kind of severity is there, that we will discuss, and then we will carry out the further session like this graph session or the LOPA, very quick LOPA session we will conduct. Okay, so that will be the post-lunch session. Right now, if this is up to this point, that means the HAZOP session part of it, we are okay with it, then we can take up just the. So we have, just to recap, we talked about the node, then we talked about worksheet, we explained what is the scenario here, and we also talked about what are the duties of facilitator and gave some clues about what to do and what not to do. Okay. Very important thing is that HAZOP session is not a design review. Okay. The number of people should be limited, participants. Typically 10, 12 participants maximum should be there, not more than that. Then we talked about the scenario in this particular node. So let us now, see, this is not a participating session, so I will dictate what is going to be the recommendation.
Yeah.
Here, the first, as I said, we are going to do the adopt without safeguard. So the scenario is hazard is that the PT2 having shut down PCB2. What will happen is that the pressure in V1 is going to rise, and the pressure, the vessel is designed for 70 bar, and the design pressure is which is coming upstream is 100 bar. So if the because of the failure of PCB2, the pressure inside the V1 vessel will keep on rising, and we do not know here what is the setting of the CSV. Okay, we also, it is not given here, we can do some assumptions, but at this stage we do not know what is the PSV thread pressure. Also, the upstream pressure of SDV1 is quite high, and if the PCB2 fails and this pressure keeps on rising, there is no other way but to either ensure that the PSV1 pressure should be high, but as I said, we will consider the safeguards later. So there is a scenario here where rupture of the vessel is possible, and as of now, we are, if suppose this is going to be an oil and gas separation situation, then if the hydrocarbon which is going to come out, if it is flammable or if it is explosive mixture, then it is a very catastrophic event. And depending upon whether the plant is located near a locality, then the consequences can be very severe. Also, we do not know what is the frequency of persons present near this vessel V1. If throughout the day somebody is present here, then there is a very likelihood that if this particular vessel is going to rupture, then all the flammable or explosive mixture, if they are going to come out, then we don't think that we have enough time for the to inform the local operator to run away from or evacuate from the situation. So this is a very sort of catastrophic event likely, and with this catastrophic event in the mind, now we discuss with the safeguards. Okay.
Yeah.
So if we take safeguard number one, there are it appears to be there are two safeguards. First safeguard is PSV1, and second
21.
safeguard is PSHH1. Okay. So if PSV1 is set anywhere near say less than the design pressure of the vessel, then the vessel can be saved. Okay, because it will keep the it will release the pressure and save the vessel. But it is again not shown here whether the PSV1 is left letting out whatever inside the vessel to open air, or it is letting out to say flared network. So if it is let out in an open atmosphere, then actually we are creating more hazard by letting out the contents of the vessel. And best way to protect this scenario could be to see if PSHH1 can trip the STV and stop fluid coming into the vessel and thereby stopping the pressurization altogether. Okay.
Yeah.
So this is the way the team analyzes by several questions and answers, and by using these guide words and these various parameters, like I mentioned that PSH at one pressure scenario is there. So pressure going high, then PSHS condition, and this, finally you conclude that the recommendation could be in this particular case that the PSHH1 should be considered as a still rented loop. That means
Yeah.
PT1, PSHH1, and SD1, all this together should be a safety instrumented function. Okay. This is the term I am telling you probably first time. Safety instrumented function is the function which will save this given vessel from getting exposed to very high pressure, and that way eliminating the possibility of failure, rupture of the vessel, even when the PCV2 has failed and inside pressure is rising. Okay, so this is the way. And the other measure, PSP1, is a mitigating measure. So while PSHH1 would be a preventive measure, it will not allow the pressure to rise. Okay, because it is shutting down the inlet pressure. And then while we are doing this kind of exercise, we have to see that some people will who are not very well initiated in process design, or who do not have the clue as to how this saving can be done. So they may question whether this LCV will have some role to play here. But as you can see, level raising is a very slow process. Level is a relatively slow parameter, while pressure is a very extraordinarily high parameter. That means the response time to pressure increase is very quick. The response inside V1 vessel will rise very quickly if the SDV is not closed, and then thereby creating a rupture scenario. While if somebody thinks that we can save the situation by draining the vessel, it will take a long time, and it will not be able to save in any way. Okay. So control of the vessel pressure by level controller is not possible. Flow control is also not going to save it, because flow control is not going to save this particular scenario. Now, having discussed this scenario, the SLR, how it is to be applied. So severity in this particular case, suppose the team discusses and considers that severity is high, and the likelihood now depends upon the likelihood question. The team will discuss whether you have any log of such failures of PCB2, because this will all have a particular frequency. Suppose you have a BPCS failing very regularly of the wall. Now there is also confusion for people. They consider BPCS failed in only wall fail or only transmitter fail, which is not correct. Okay. Once we say that this failure has happened, we consider the entire loop failed. That means we don't distinguish between a transmitter failure, the BPCS failure, or the wall failure. We say it is failed, it is not available, so that particular activity is not going to happen, and we assume that the moment we say this PCB2 failure has happened means the pressure inside keep on rising. This is a drawn conclusion. Okay, so we are not going to debate about it. So now the likelihood question would be answered only by the operations people who will be able to tell that this kind of failures of BPCA, whether it has happened in the plant before. Suppose this has happened in a plant once in 10 years or once in what kind of frequency it is, that we can find out from the logbooks or past record, and then we can assign depending upon that frequency the SLR, and then once you multiply S and L, you get the rating for risk, and based on this risk rating, and in this particular case, because this particular one is a very severe case, in case of the failure of the rupture of the vessel, what the catastrophic incidents will be there, there is a nearby some community or some colony is there, all the people might get exposed to toxic. If suppose the vessel is whatever is going to be spilled out is toxic, then it can happen that the entire particular colony can get exposed to severe environmental hazard. So based on this, the question the chairman will ask or the facilitator will ask it, what should be rated as? And suppose initially the SLR is done as very severe, and after considering the safeguard, they give credit to the safeguard. But here in this case, the safeguard we are not able to give credit because in case of safety wall, there are only two safeguards. One is safety wall and second is
Yeah.
So out of that safety wall, we cannot take credit because we do not know whether it is giving the whatever is coming out of the ruptured vessel, whether it is left to open atmosphere or if they if we to a closed circuit. That's why we have to consider that only one safeguard which is available to us is this SDV and PSH2. And in that case, if we want to ensure that it all functions when it is required, then we would recommend it as a please look at making the PSH2 loop as a safety critical. That means still may be calculated for this particular assessment may be done for this particular loop. This kind of thing. Now, this is the very quickly I captured that this is the way the discussions are there, and this is the way the recommendations will come out of this. Now, here people, as we told, we have to avoid lot of unnecessary discussion. Like people may say that we will take a software alarm of this and we will do it like this. These are all type of discussions which are unnecessarily meaningless digressions of the discussion, because as I told you, design review is not to be done in case of absorb session. Doing this kind of thing that let us try to add a software loop and this and that, these should have been thought of at the time of design review, not at the time of hazard. Okay. So after this discussion, most appropriate recommendation could be, please see if ESH2 SDV loop can be considered as a safety loop. But if it is safety critical, then please do the analysis of this loop or LOPA analysis of this loop, or look at whether it can be converted to a safety still loop. Okay, this kind of recommendation can come out of it. Okay, so this is the way the HAZOP section comes out, and then for subsequent to action report, what it will do, it will call for a, because HAZOP is a session which normally is a conclusive session, and after HAZOP recommendation, the next session needs to be addressed. Many people nowadays also combine HAZOP and LOPA together, but depending on company philosophy. whether they are going for low pass or they want to do quantitative analysis, that again is a issue. So the action taken report would only, the recommendation would be only to see whether this group can be considered as personal rating. But the action taken report could be, if the risk graph method is to be, qualitative method is to be used, then a separate assessment, single assessment session is to be done. If LOPA is to be done, I think it can be combined with the head-off session, provided there are certain prerequisites. What are the prerequisites? See, what question did the consultant ask? Do we have a record of how many times this group has failed? Okay. So the people tried to search that record and they did not find any specific answer to this. That's why it has to go to the next criticality assessment of the LSHS. Okay. So what you need for LOPA session is uh, being a semi-quantitative analysis, you need a typically what they call a terms of reference. Okay. Now, what are terms of reference? Terms of reference are company guidelines on what are the ways we should consider. That means if you are going to consider for LOPA, typical uh, failure rates. That means, suppose there are two or three safeguards here, say Shakti Wall, and the second one is the LSHS. So you will have to find out that what would be the failure rate of these things if your particular logbooks or your past track record is telling you that, then you can use that record for deciding the frequency or the failure rates. But if you do not have that, then you have to go to certain standard available data in the industry, like CCPS. I mentioned in the morning this particular name, CCPS, Center for Chemical Processes Safety.
Yeah.
They have given a standard, industry standard references. So people tend to use it many times in absence of company specific data or industry specific data. They go and use this CPS data for failure rate and then conduct a typical LOPA analysis. Okay. LOPA analysis we are going to do today very quickly after some time. Not very detailed, only one deviation we are going to consider. But before that, let me show you if that company has a standard method of doing a qualitative risk analysis, that means risk graph, then how to do it. Okay, just give me 2 minutes. I will just study this particular risk graph and then I'll explain it to you in detail. Just study it for 5 minutes. Okay. So typical risk graph is shown here. Okay. So risk determination of all risk receptors PEAR can be done by risk graph method. The risk graph of people is as below. So this particular slide is shown risk graph as applicable to people, that means persons, this risk receptor as person. Okay. So this is this is given by IEC itself. Okay. This particular risk graph is given by IEC itself. And now the information we derived from the absorption that we are going to use here. Okay. I'll explain you how it is to be done. Starting from the left of the screen, okay, starting point of the risk reduction, CA, CB, CC, CD. These are the four parameters. These are the four parameters. Okay, that is severity parameter. Okay, criticality or severity parameter, CA, CB, CC, CD. Now, if you see your particular HAZOP report, okay, just if you see the HAZOP session, what you did earlier, here, if you feel, I mean, this is something open discussion. I'm not going to dictate a specific thing, but you can all think about it this way, that in this particular node, what we have, by the way, the slide line. Yeah, in this particular node, the criticality of this particular safeguard,
Yes, etc.
yeah, PSH, whether it is, what do you consider it? The severity will be CC, CA, CB, CD. Suppose you say that CC, CD is the highest criticality and CA is the lowest criticality, then in that case, go back to that test. Yeah. So suppose you consider medium sort of thing, CB. Okay. CB is the frequency which you assign here. Okay. And now what is happening here is that there are two, once you say CB is your scenario, then there are other parameters like FAFB, PAPB. I'll explain what are those. And on the right side, we have W1, W2, and W3. Okay. These are W1, W3, W2, W3, W1, W2, W3 are likelihoods of that event occurring. Okay. Now, criticality is known. FAFB is the parameter we typically call it that
Exposure time.
exposure time. That means the operator is going to be available near the site of accident or not. So in this particular case, we take everything as FA. Okay. So CB, FA. Now PAPB is again a dimension where we say that if that person is available, whether he has got time to run away or evacuate from there, or some way can we contact him and tell him that there is some accident going to happen in that particular area, and then he can evacuate, and there all so many possibilities need to be there, so many requirements are there, like you should be able to communicate to that person. Secondly, he should have escape routes from there which he can use and evacuate from there. Okay, so once you have this CACB and then you have this FAFB, then finally you land at PAPB. Okay. And suppose your event frequency is going to be W2. In that case, what will happen is you end up with SIL2. Okay. SIL2 you are ending up with. Okay. So in this method of analysis, you are directly getting the SIL2 as an answer. Okay. While in the next thing which we are going to study, this LOPA, there you have qualitative, that being a more semi-qualitative method, you have a more resolute method of addressing this particular issue. Here, what is happening is here we are straightaway landing into SIL2 as the answer. Now, if you study this particular risk graph, see, you have seen that there are other safeguards available and we are not able to give any credit to these available safeguards in case of risk graph. Okay. Because there is no way we can assign any credit to that. That's why this particular thing remains qualitative only. We cannot end up with any numerical answer to in case of this graph. Okay. So first, there are safeguards which you have not taken. Two drawbacks of this graph worksheet is this graph method is that you cannot take credit of the existing safeguards. And secondly, you do not end up with any number like whether it is a
100 and
still whether risk reduction factor is 100 or 30 or 50 or such thing. It gives you that it is a only event. Just SIL2 it will take. So now SIL2 starts from 100 to 1000. So it is very broad design it can be. Okay. See, as we go into detail. Okay. But here at least it gives you the SIL2 type of indication it gives. And with that, if it is about 5 years ago, this SIL2 was good enough, but nowadays people would like to really design that particular safety instrument at position. That means we'll have to select a proper transmitter, a proper wall, and all these put together should give that risk reduction factor. Okay, that is not possible in this case. They will just say that this is a SIL2 loop. And if somebody questions how do you calculate the risk RRF, you will not be able to do that in case of this graph. Okay. So the best thing now, why this graph again is called quantitative? Because as a result of this graph method, you will come to know whether your risk is falling in SIL1, SIL2 or SIL3 category, but you won't come to understand numerical value of the risk mitigation factor. You also can't take credit of existing safeguards with the process design. But still, this technique is quite good for initial decision making and quite popular. Okay. Now let's come to the second method available to us. LOPA.
Layers of
protection analysis. Now here we are going to discuss layers of protection analysis used to our particular example of HAZOP. Okay. Now we are going to take again that LSHS loop. We are going to see whether it will fall in SIL1 or SIL2 or what it is going to do. So how we are going to do it? We will first let us understand this worksheet. Okay. So the worksheet is to be understood like this. That typical MSXM LOPA worksheet. Here what we have is
here we have project, then SIP number, what it is, then SIP tag number. What SIP tag number is, you need to note down that. Then SIP, what is SIP description? Means SIP description is what it is doing. So in our case, whenever the pressure goes above 70 bar G, the PSH loop is activated and it shut down the SDV valve to stop the flow. Okay, so that will be our SIP description. And event consequence, you can write down from the HAZOP that if the consequence happens, then the vessel may rupture due to the more pressure, high pressure. Okay. Now there are four.
Most important parameter here when you before doing LOPA is that you must know your tolerable frequency. Most important thing before starting. So your corporate guideline either should specifically say that your tolerable risk is so and so. Okay, they will give you a number here. We'll explain you that also. And then once you know that number, then you have to put it in this worksheet.
You need to put not put in here severity. You need to enter the severity from the table there. So according to the severity, it will automatically give the frequency and category according to the risk matrix.
We have for building this worksheet, we are using CCPS guidelines. So those guidelines are picked up here. Okay.
Yeah, so the risk matrix, whatever category it comes under, it will show that, and frequency it will show. So here there are three types of tolerable frequency. Means you come means I'm taking you back to the slide for that. What is risk? In that, sir explained that one line is of a tolerable risk. Okay, so that here also tolerable frequency. Each and every organization has a different tolerable frequencies. Okay, so accordingly, we need to put down the tolerable frequencies are of three types. That is health and safety, then tolerable frequency for environment, then tolerable frequency for finance. Okay, asset.
Hello. Sorry to interrupt you, sir. Can you please use the pointer so that people, participants can easily understand?
Yeah.
Okay,
So here,
thank you.
here, here there are these four columns are the category, frequency, severity, and category. Okay. Now, according to the severity, what severity it comes, we need to enter it from the table, that is risk matrix, that which severity it is, that is 2, 3, that we discussed in HAZOP. Okay. So according to severity, it will take the frequency and it will categorize it.
The frequency will be decided once you enter
Yeah.
the parameter.
Yeah.
And then that tolerable frequency has a big role to play, because that is what you can tolerate. Anything above that you are not going to tolerate. So ultimately, what is going to happen is this tolerable frequency will come in the denominator, and the frequency which you will generate out of this various columns shown here, that will be the numerator. So finally, you will get the risk reduction factor based on this. Okay. So let us do all this table is populated with CCPS guidelines. The terms of reference are to CCPS guidelines. Now let us go step by step. As Purva mentioned to you, he has given the description of the particular initiating event, and it was saying that if this particular event happens, what is going to happen? That the wall has to shut down to stop the incoming fluid, incoming pressurizing fluid. Okay. So now unmitigated event frequency. First column, what
this
is
one,
here?
this one.
This is the thing which is about the BPCS. Okay. So the BPCS, that means the control system. See, in first you please understand, BPCS is control system layer, which is layers of protection. If you see, it is the second layer of protection. And safety instrumented system is the fourth layer of protection. So here, in this one, we are talking about frequency of failure of the BPCS layer to determine the risk reduction required for the safety instrumented system. Now, as per CCPS, generic industry standard says that EPCS can fail in once in 10 years. Okay. So 0.1 is the factor for BPCS. So you write 0.1 in this particular first this one you write 0.1. Okay. And then subsequent condition modifiers is one column. In our particular case, it is not applicable, but I explain the usage of these ones. Conditional modifiers are typically conditions which can be used for the case of person available or not available. Okay. Person whether he is going to be near to the accident site or not, that kind of
and
thing.
how much hours he will be there.
That kind of thing you can decide. And then time at risk. Time at risk is suppose that person is available, whether he will be full time there or he will be part time there. That again is a factor which, and CCPS has got a guideline for that also. If the person is available throughout the day, then it is 1. If he is available for 4 hours, then it is 0.5. Like that you have to see. Okay. So that parameter also can be taken. Then IPL 1, IPL 2, IPL 3, IPL 4, IPL 5. These are the various independent protection layers available for the PFD calculation. Okay. Now, these are the various existing safeguards. That means safety wall, or if there is any other, suppose that level valve was doing something, then that could be a second IPL. Okay. So ultimately, finally, what you do is, this is inventory kind of example. So LOPA is an inventory example. So what happens in inventory? That you multiply all these columns, okay,
Here it will come.
and then finally that numerator will come in the intermediate event frequency, and once you divide it by the tolerable frequency, you get the final mitigated event frequency. Okay.
Yeah.
This is the way. The moment you put various factors there, this is not this particular table. This is just a screenshot, so we will not be able to do actual calculations here. But the moment you put all these factors here, the answer is shown to you in the mitigated frequency.
Risk reduction factor.
Straight away you get that. Okay.
Yeah. What is that?
It will come as a PFD average, -4 something.
Yeah. So this is one type of initiating events. There are other initiating events that it will come here, and all this mitigating initiating event frequency will be summed up, and it will come down.
That means if the same consequence is going to happen because of some other events also, then they will be added. If there are separate events going to happen, then it will not be added. For each separate event, there will be a separate sheet like this.
Yeah,
okay?
yeah.
So this is the way LOPA is done, and in the available time and in the given limited LOPA worksheet, we can explain you this particular like this, and this will be now the final calculation of the say, suppose it comes to say risk reduction factor of 100. So now you have to decide that the PSHH loop will have to be designed for risk reduction factor of 100. And what does that mean? So now you have to write a safety requirement specification for this loop. Okay. So that safety requirement specification, Apurva will show you.
Yeah. Some detail. Yeah, this is some detail about LOPA. What we explained, that is only there here. Okay. Yeah. So what is a end user safety requirement specification? Now we have got that one this particular loop must have risk reduction factor of 100. So now we need to define the safety requirement specification for that loop. So that is one is functional description of all safety functions. Okay. So functional description we need to include in that, elaborate into it that if this pressure goes high, then it should stop the flow, and so that it doesn't over pressurize the vessel. Okay. Now another is safety integrity level. That is whether we require SIL 2, SIL 1 like that. In this case, we have SIL 2. So that's why we will write SIL 2. It is. Now required risk reduction factor or PFD, PFH. So that it comes as 100. Now we need to define energized to trip or de-energized to trip. So
there are two philosophies.
There are two philosophies that if we de-energize to trip the valve, then the pressure will be controlled, or energize the valve and then pressure will be controlled. It is de-energized to trip. Now here there are three types of demand modes are there: low demand, high demand, and continuous. Right now it is low demand because it is the low demand. Low demand is basically demand that comes once in a year. Okay. High demand is more than one time in a year, and continuous demand is continuously demand is there. Okay. In process industry, we can have a low demand or a high demand. Continuous mode is for the batch plant, automotive batch process like that. The safe state for each safety function, that is safe state is whether it is open or closed. So safe state here is a closed. Okay. Startup, restart, reset functionality, that you need as a user you need to define that what will be the startup procedure, what will be the how it will be restarted once some fault comes, then how it will be restarted, and once fault occurs then how it reset functionality is there, you need to define that. Then maximum allowable spurious trip level, that you need to define.
This is a very important thing see, we always, till now, we have been talking about only safety, safety, safety. But for the user or the owner of the corporate entity, it is more important for them to run the plant, because then only they can achieve their operating factor, and then only they can make money out of that plant. So they define this particular thing, that we do not want maximum. That means they say that serious trip level should be not more than once in 10 years, something like that.
Yeah.
So that kind of thing that we should obtain from the corporate entities. And then other things like
environment conditions like temperature, EMC, humidity, vibration. So basically what temperature maximum, what temperature limit should be there, then EMC, then humidity, vibration, that should be within that the hardware which you select, that must be within that limits. So that are environmental conditions you need to define. And then bypass philosophy, what is the bypass philosophy? So that also you need to define that. But if say I need to I want to maintain, I want to maintenance, I want to do maintenance for say one positioner, then what should be the bypass philosophy? All that things you need to mention, whatever it is there. Okay.
So this is a comprehensive,
Yeah.
I mean top level comprehensive safety requirements specification. There are so many. Actually, it is hardly we are showing 10 or 11 things, but there is
more than 20.
Software we have to try so many things. Lot of logics we have to detail explain.
Yeah.
So that is not possible to cover in this.
What is process safety tank?
Yeah.
And yeah.
So many things are there.
Yeah.
So that we cover it during in our detailed course. But here, because of the paucity of time, we can cover only this much. But you must this safety requirements specifically is a very important thing. And as of today in India, at least I can tell you, it is an ignored item. People do not write. People tell to their consultant or the system integrator that you decide it. How he can decide whether you want a load, whether you want a energized to keep or de-energized to keep, whether you want a what kind of furious strip you want. All these things he cannot decide. Bypass philosophy, he cannot decide. So this is something you must get from the end user. Then only you can get it.
Yeah.
Okay. Then last thing, this is the safety function. Okay. The safety function consists of three subsystems: sensor subsystem, logic solver subsystem, and final element subsystem. Now, most of the times, the safety instrumented function is normally inside a hazardous area. So barriers or some such accessories will come into picture. They need to be grouped within the sensor subsystem or logic solver system, depending upon which side they predominantly belong. And then you have to take a failure rate of all these sensors, logic solver, and final element, and combine these three together and calculate the whatever is the, whether it is meeting the risk reduction factor given by the your consultant or whatever.
So if the whole ship has to be qualified for SEAL 2, that is risk reduction factor of 100, and say that sensor subsystem is selected for SEAL 1, and logic solver and final element are for SEAL 2, then it will not fall under SEAL 2 category. The whole of the ship has to be sensor subsystem, logic solver subsystem, and final element subsystem has to be SEAL 2 compliant. Then only the whole ship will become SEAL 2 with risk reduction factor of 100. Okay.
And only taking a SEAL 2 certified all the three things is not good enough. You have to calculate risk reduction factor and establish that it is meeting. Because SEAL 2 is a large range. Anything between 100 and 999 is SEAL 2. So you have to see when if your risk reduction factor is 500, then you must meet the risk reduction factor of 500. SEAL 2 is 200 also, but that will not do.
Yeah.
Pre-design is a very important step in this.
Yeah.
Next slide.
Yeah. So seal design and seal verification. So in previous slide we show how SIP looks like. Okay, and seal determination we have obtained whether it is seal 1, seal 2 or seal 3 SIP, and its risk reduction factor. This is RRF value is mentioned in SRS document. Okay, so whatever value is there in SRS, you need to fulfill that. RRF can be equal to and greater than it has to be. Whatever SIP you have designed. Before actually implementing the SIP, one has to design the SIP or carry out seal design by selecting architecture of each subsystem, meaning whether we are going to have redundancy in subsystem or we are going to use no redundancy as required by IEC 61511 standard. Also select IEC 61508 compliant subsystem components, certified components of each subsystem, and finally verify by calculation if in the given situation meets target RRF requirement, the architectural constraint requirement and systematic capability requirement. Okay, so to for SIP to qualify as a required SEAL 2 or SEAL 3, there are three criteria. That is, one is RRF requirement has to be met. Second is architectural constraint requirements has to be met. That is, if in case of SEAL 3 systems, we need to have a redundancy, that is 2 out of 3, 1 out of HFT has to be 2 out of 3, 1 out of 2. That HFT is a hardware fault tolerance requirement. So that constraint, architectural constraint requirement has to be fulfilled. And third is systematic capability. That is whether your the selected sensor, logic solver, and your final element are SC2 capable or not. That has to be there. That has to be ensured.
Integrator has to be certified.
Yeah.
Function FSM certification.
And the system integrator who is doing the integration work has to be FSM compliant and certified. Yeah. So this system capability requirement you can get it from the SIL certification which the manufacturer provides. Okay. So if all the three criteria are satisfied, then we declare that SIL verification is completed. Okay. SIL verification calculation nowadays is done by using software. Yeah. So this SIL verification is done by various softwares like Excellencia, then SILSET is there. Then other sophisticated softwares are also used. Okay, so we can do that with those softwares.
Or you can do it in Excel table also. That's possible. There are simplified equations given in the standard, which you can actually in the Excel spreadsheet you can prepare your own one.
Yeah.
It's a little cumbersome, but it can be done.
FAT, IFAT, and SIL validation. Okay. So, as you know, in the life cycle of IC 61508 and 61511, these steps are also important: FAT, IFAT, and validation. Okay. So, after SIL verification and all these things are done. Okay. Then the user. The integrator will share will prepare the FAT and IFAT. IFAT is an integrated factory acceptance test that is integrated with all the sensors, logic solvers, and final elements, and it are tested at one particular location. Okay, and it is done to check hardware and software performance, and similar way hardware and software performances are checked with respect to whatever the safety requirements are given in the specifications, and accordingly it has to be checked. And FAT or IFAT procedures are submitted by system integrators according to safety requirement specifications, and after that they will also internally check, and they will submit whatever they have checked, and whether it is satisfactory or not, and then they give us the one date that they need to conduct a FAT or IFAT, and then a third-party agency will go and they will conduct according to the procedure, and
client must be present.
Yeah, and client must be present during this FAT or IFAT. Okay, so you know that FAT and IFAT are a pre-installation before installing at a site. These are done in factory premises. And another thing which is there, it is a SAT, site acceptance test. That is, this test is conducted after installing the system at the site, and it is also known as a validation. Okay, so whatever you have integrated, whatever sensors and this you have used for integration purpose, that needs to be validated, and tests are performed at site, and the report has to be generated for that. Okay.
Okay. So this brings us to the end of this particular module. The part.
Okay. This brings us the end of to the part 3 module.
See the questions.
Yeah. Shalini ji, you can poll down. We have 5 minutes. Okay.
Okay.
Yeah. Yeah. So we can stop the polling. Okay.
Okay. I'm just closing the polls.
Yeah, you close. I will let the answer know. You have closed the poll, Salary?
Yes, close that poll. Now you can put in the answer.
Okay, okay, one. Yeah. So, what is meant by qualitative risk reduction technique? Okay. Qualitative risk. Okay, so here the answer is one. Instead of reaching numerical answer, you reach a somewhat inaccurate answer. So, so basically,
The third one.
third one, yeah. In qualitative risk, yeah. So first question, the answer is three. In qualitative risk analysis, your end result is subjective, and if you change the team of personnel doing the analysis, answer can change. Yeah. So basically, as sir told that you can get seal one, seal two, okay, but you cannot quantify that whether it is what it is 100, 200, 300, and also the if team changes, then the perspective of that member change, and it can go seal two can go in seal three also. So it is that. And second question is which risk reduction technique is termed as semi-quantitative, that is low bar, that is third number. Okay. Now with this, before starting part 4, we will have a 10 minutes break. Okay. Okay, Shalini?
Okay, sir.
Yeah. Yeah. Thank you. Yes. So, shall we start? Yeah. Okay. So, last part 4, that is certification and application.
Okay, here what we are going to learn is, see, you are when you are using a safety system as per the standard should be compliant. Okay, that is compliant to the standard. But you yourself, if you do not have that much knowledge, most of the users they don't have that much knowledge. So compliance they cannot uh, understand. They cannot verify themselves. That's why certification comes into picture. The third party like TV, Ristology, Exida, these people they certify various devices or systems or solutions, and then they that is considered as these bodies are well-known bodies. They certify these whatever the design has been done, and then they certification that's the way that comes into the industry. Okay, because compliance otherwise the end user cannot decide. Okay, so why synthetic is required? Because the end user or the consultant carrying out the design before implementation must know following three things about the device and component system they are going to use, realizing the safety system as required to meet safety requirements specifications. The reliability of the device in terms of failure rate, and the failure rates are mentioned or called lambda DD, lambda DU, lambda SD, lambda SD. What are these lambda businesses? That will tell you in a detailed course. But as of now, suffices to understand that these are the terms which are used in failure to indicate the failure rate, and these are used to calculate the risk reduction factor. The architectural constraints with HFC value of each shift what you have designed. Then systematic capability value. Systematic capability value is the functional safety management compliance. That what is achieved by the integrator and the various parties which are taking part into the design. Okay, so these three things you must know. That's why you conduct these skill certification. Okay, so let us learn about skill certification in the following slides. Next slide, please. If one uses non-certified components, devices, or systems, then one may not have this information and the six verification step may not be fulfilled. Okay. Therefore, certified components are used. See, as I told you, standard does not require certification. And in IEC 61508 standard, nowhere it is written that you must use certified components. They say the components used in the safety system should be compliant items. Okay. But they don't say that it has to be certified. But because there is no way to find out whether it meets your requirement, because the end users or the system integrators, they may not be knowledgeable persons, that's why certified components are used. A third party certifies these components, and that is the way you end up with a certified system, still certification. Approved certification bodies like ICDA, Ristology, TUV, etc. publish this information by issuing SIL certificate. A typical certificate is shown in the next slide. But just before that, let me tell you about more about this body. These certifying bodies are members of a federation called International Accreditation Forum, and this again is based at Geneva. And from there are various bodies like TUV, some of these examples which I have given, and these are the notified bodies. In India, the body is NABCB, which is under the Committee Council of India, which is a body which you are a certifier, like I am a certifier in India. So I am supposed to get accreditation by NABCB or any other IF accredited body. So we have obtained accreditation from American Association for Association accreditation. That is the way our company is affiliated. So approved certified bodies need to be there to certify these various things. Okay. So that is a necessity because of the third party situation. That means standard does not demand certification, but standard demands compliance. And in absence of third party certifiers like CDAT, UNI, Technology and all, we cannot just trust the end user of the. Suppose there are people who self-certify their product, but nobody will trust them because they will have their vested interest in selling their products to you. Okay, next slide, please.
Yeah, so this is typical seal certificate. Okay, this is a certification of a Inverson's Rosemount pressure transmitter 3051 series. So, just I will explain that. See here, systematic capability is written here SC3 seal 3 capable. This transmitter can be used for seal 3. This transmitter is seal 3 certified. Now, random capability that is a
See, morning we had explained you three types of failures: random failure, common cause failure, and systematic
system.
failure. So this certificate actually is giving you a clear certification for all these failures. Random capability they are saying
Type B.
type B11. Okay.
No, yeah.
And they are giving a
This is seal 2 at HFT 0. HFT is a hardware fault tolerance. Okay, so seal 2 at HFT 0 and seal 3 at HFT 1, that is 2 out of 3. If 2 out of 3 transmitters are used, then HFT can be met as 1 and it can be used as a seal 3. And
because one
two
can
units,
do it after I'll explain it just after some time. And the third thing is SC3, what Apurva read just now. SC3 is the systematic capability. Okay. So we have in this certificate, all the three things are mentioned. The name of the company which has produced this particular product, that is mentioned. The model number is mentioned, and then to which standard it is certified, that is mentioned.
Yeah.
And in that standard, it is saying that parts 1 to 7. Morning we learned about there are 7 parts in IEC 508. So for all the parts it is compliant. The systematic capability of this particular company is SC3. That means their systematic capability, their work processes are aligned to systematic capability 3 standard. Okay. Then random capability is a type B in a minute. What is type B and type A? That I'll explain in a minute. But before that,
the main important thing here is validity. You can see in the
actually validity is not very important. This one validity is important from commercial point of view because these people they are certifying. They would like their business to grow and continue. That's why they keep on keeping it for 3 years. And there are chances that standards may undergo revision or the assembly lines may undergo revision. That's why this validity is important. Okay. So these are the things that type A and type B is type A means that something of which every way, what are the failure modes that you know, every failure mode is understood. Then that is it needs a lot of discussion. Right now I'll be able to tell you only this much because in detail that will be explained in a detailed course which is a 3-day course. But right now I can explain you only this much. And type A and type B types of devices are there. Then same way, group 1 and group 2, this is also a concept which will be explained in detail in the detailed course. But this is, in this case, this particular transmitter is certified by both standards, one is as well as group. We'll explain it in the detailed course. Okay.
And also in that it is in small handwriting it is written for models where SFF is greater than equal to 90%. That also.
But SFF is a concept which we'll explain in detail. Right now it is difficult to cover.
Yeah.
Okay. Then I will show you. There are safety functions is written here and applicable restrictions. Please read that. It's not readable here as of now, but restrictions are there like temperature. It should be within this temperature. The usage should be there. like that.
Here it is written, this unit must be properly designed into a safety instrumented function as per the safety manual requirements.
Yeah. See, now this is a safety certificate. As I told you, Exida has certified this. So Exida is a certifying body. It has ANSI is the ANSR. This ANSI is the
Yes, this ANSI.
ANSI is the certified body of America, which is which is so Exida is certified, and the certifying body is ANSI. Exida is the certifier, and then it has given this certificate as one of the documents. There are actually three documents in this certification business. One is the certificate, which is the final product. Before that, the company which is like Rosemount here or Emerson, they have submitted this product to Exida for certification. So Rosemount has to publish a safety manual and give it to Exida. Exida will study this whole work processes, the calculations, everything they will see, and then they will certify as per component of it, and then they will issue this certificate, and a certification report also will be issued by Exida. So there are three documents required to be there in a certified device. Okay, either a PLC or a device or a sensor. People have a lot of misconception. Lot of people ask me this question. Ours is a mechanical valve, so it should not be certified. That is not correct. Every product which is used in a safety loop has to be certified or compliant, and that compliance only way to ensure compliance is a certificate. That's why certification business has become popular. So this all the three subsystems and all the accessories of the three subsystems. Suppose your final element is a valve, and that valve is a has a actuator. That actuator is getting actuated to a solenoid valve. All the three have to be compliant and depending upon SIL 1, SIL 2 or SIL 3, whatever it is. And in calculation, parameters of all these three devices will be taken. Okay, that's it.
Yeah, this is the typical SIL certificate page 1. Now it will be page 2. Okay.
And the page 2, you will get all these
failure rates.
Okay. It's like it's not very clear, but it is lambda DD, lambda SU,
Yes,
you can see it all that, and their values are there. So this will be explained in detail in a regular course. At this stage, it is difficult to cover it in small time. Okay. There are concepts like SFF, then there are concepts like Group 2H, Group 1H, and all that will be all covered here in the detail. Okay.
What is what is another mandatory document of certified company? Other important document must be available from a certified instrument device system supplier is safety manual. Okay, so we have got SIL certificate. So the safety manual also needs to be prepared and done by device manufacturer, or if some
like how to install,
how to install, how to proof testing.
Proof testing is again something very important.
Yeah.
We cover it in detail.
Proof testing is also a big topic, so we will explain it in our detailed course. Yeah.
Okay.
Yeah. So, Shalini ji, we have two questions, and you can start the polling. We will give them 5 minutes. Okay.
Okay, sir.
First question: what is meant by certification in safety, functional safety? That answer is 1. And for question second, which minimum 2 documents must be there for functional safety certified device? The answer is 3: safety manual and safety certificate. Okay.
So we thank all the participants for their cooperation, and we would like to declare that this particular course ends here.